Vous êtes en direct, voilà.
Très bien. Le lien, il est sur notre chaîne.
Le lien, il est sur... non, il est sur ma chaîne à moi.
Ok, très bien.
Après, il faudra qu'on le transfère, évidemment, mais comme j'avais pas les codes de...
Non, mais t'inquiète pas. Faut-
Voilà. Et puis, du coup, ce qui est vachement bien, c'est que dans le programme, dans la page PAW, j'ai intégré la vidéo YouTube. Donc, quand tu ouvres PAW,
Oui, dans le lien au-dessus, là.
Ouais,
Ouais, j'ai vu ça, ouais.
ouais. Non,
Oui,
non, même,
non.
même en dessous, je l'ai intégré.
Ah, d'accord.
Hein.
Yann Orlaret, 4 abonnés. Nage de printemps, c'est toi qui as fait ça?
Hein? Non, ça c'est. Non, là, c'est pas celle-ci. Alors, je t'avais envoyé le
Ah,
lien, Sébastien,
oui, la
dans un
dernière
mail.
fois, en effet, je vais le retrouver.
Non, mais si tu veux, je te le renvoie. Euh, je te le renvoie. Ou si tu vas sur pao.gram.fr,
Mais bien sûr,
tu as, il est même intégré maintenant dans le. Tiens, du coup,
mais
dis-moi
bien
si ça
sûr.
marche. Ouais.
Ok,
Ok.
parfait. Live on YouTube.
Voilà. Non, mais si tu veux, je te le renvoie.
Ok, parfait. Juste, je teste. Effectivement, on peut le voir depuis le début.
D'accord.
Très bien. Parfait. Donc ça marche bien, ça, ouais. Ok, ok. Très
3,
bien.
4, 5, 6.
Ouais, on t'entend, Steph. Oh, on a un pic de 7 lectures hein, sur le stream YouTube.
Et il y a déjà 4 likes.
Ah, ah oui, c'est le début de la gloire, là, à mon avis.
Morning, everyone.
Good morning. Who's speaking?
Bonjour tout le monde.
Bonjour. Okay, good morning everybody, and good afternoon also for our Chinese friends. And welcome to this new edition of PAW, the Programmable Audio Workshop. My name is Yann Orlaret. I'm the Scientific Director of GRAM, a national center for music creation based in Lyon in France. GRAM is an institution which is dedicated to the contemporary music creation, where artists, musicians, and composer works together in close cooperation with researchers, particularly in the field of computer music. Among the various software that we developed here at GRAM are the low latency server Jack 2, the dynamic music score system InScore, and the Faust programming language. All these projects are all open source. Some few words about PAW. The goal of PAW is to bring together designers of programmable audio hardware and designers of tools and programming language together. The day is organized in the form of 6 workshops. These workshops are quite concrete and technical, and they are all based on the theme of this year, which is modular audio synthesis and programming. And this is a very interesting concept, not only because there is this revival of modular synthesis, but also because this is a very wide range concept that interests architecture, music, mathematics, computer science, and engineering also. And if you look at the first version of the ENIAC computer in the late 40s, it really looks like a gigantic Moog synthesizer. And the concept of programming by patching modules is not only of musical interest, it's of interest for many kinds of programming. So this is why we're so happy to have this theme this year. So the first talk will be by Max Brucker. Max is an electronic musician, computer music designer and sound engineers. He writes music and software for contemporary music and live performance, in particular for dance. On stage, he uses software such as Max or Reactor associated with homemade instruments, modular synthesizer, and various sensors to elaborate his idea. And he teaches also signal processing and sound design at university and art school. And he collaborates with Graham since many years. And in his talk, he will explore various conditions of interacting, playing, and composing with this kind of approach. So, Max, it's to you.
Hello, everyone. Nice to see you all on this channel. I'm really honored to be presenting this, opening this PAW session for 220. As Jan said, it's been a concern for me to try and find some interactive systems, because I'm pretty sure that most of you who use computer music softwares and video softwares, not only, but also hardware stuff, are always in this kind of situation where they have to change protocols to send any information from one place to the other. So this is a kind of hassle. It's always been. So my main question was, what kind of protocol is the easiest one? So these past years, we all know MIDI as a protocol, because this is one of the most famous ones since the 80s. And the MIDI system is really one of the most reliable ones, because all of you know that the MIDI is something that is written in the hardcore of all your OS computers, your OSs of your computers. And along the years, MIDI has changed, and one of the most famous ones now is called MPE, for a multi-channel and complex MIDI system, which I won't be talking about because I don't have any of those to show you right now. I would have if lockdown in France had cut us from the studio, so I'm at home. So I won't be showing you any hardware system neither, even though I have a Eurorack system, which is really nice. So I will be talking about Eurorack systems, but particularly in VCV rack. So coming back to the protocols, one of the major problems that I had along these years is trying to send information between one software like VCV rack, another software like Max MSP, or it could be Pure Data, Ableton Live, because Ableton Live, which is a really very famous DAW now, but I use it mainly because you can write your Max patches and put them inside Ableton Live. Well, there are some issues there, but still, let's not talk about that part. And I wanted to talk about also video, because I'm going to show you how to interact with the video system too. So the first thing first, I'm going to show you, for those who are not familiar with VCV Rack, let me show you, present a screen, and let me show you this first. So you should be seeing shortly the main page by VCV Rack. So VCV Rack is, as it says on the main page, is a Eurorack simulator. So what is Eurorack? It's actually modules that have functions, just like in programming, general programming, but this is older than computer programming. This is where Maximus Peace probably got its first ideas from. And VCV Rack is sort of an emulation of all types of modules. The nice thing about it is that it's open source. There's a very big community of people working on it. And it's actually easily hackable and easily usable to produce music and video. You'll see some people doing that too. So first thing to do is probably to install VCV Rack and create an account. So I'm already logged in. And well, Rack doesn't have all the modules that I'm going to show you. So you will need to install a library, some libraries, in fact, that you can find in the library section. There's a library here. You can have a look at that. And so the first thing that I will be using is a library by TrowaSoft. So TrowaSoft is a really nice library using OSC, Open Sound Control, that was supposed, by many people said that Open Sound Control was supposed to be the new MIDI. So it's a network protocol to send information from one place to the other. Well, in my humble opinion, OSC never achieved that properly, because OSC, it's not dead yet, but it's a bit complicated to use. It's not as intuitive as MIDI would be, though MIDI also has its hassle. MPE, which is the MIDI extension now, especially since Ableton is going to implement MPE within its software. Maximus P has also done that. It's going to be probably one of the next steps in controlling your softwares. Well, TrowaSoft implemented OSC within VCV Rack. So you will need to install this library. Then the other one is, one of my favorites, is Audible Instruments. Those who use Eurorack are actually probably familiar with Mutable Instruments. It's the open source part, and probably the most intelligent, to my sense, Eurorack system ever made, because Émilie Gillet has been developing these modules in hardware, all open source and open hardware. So you will find all over the world different types of different variations of her modules, and this is the software application and software fork of it. So I will be using it, and there's this very nice library by Bog Audio with tons and tons and tons of modules, and they're really intelligent. And this is probably the best way to go into synthesis, because it relies on very old school definitions of stochastic synthesis. So, and the last library will be Plateau. And Plateau, like a plateau in French, is another library, and there's one really nice reverb that all the VCV Rack fans use, is the Plateau Valley, and this one is, it's a plate reverb, but it really sounds nice. So let's go on. Let me show you VCV Rack. So this is VCV Rack. This is the first patch that I'm going to show. VCV Rack actually is very simple environments where you have a blank page with a few modules, but you can put your own modules inside, the ones you had in your library. So once you've installed your library, take a look on the internet for that part, because this is very well documented. You can put them by right-clicking in your window and just clicking on the library you want. So in this patch, I will be sharing all of this. I installed the TrowaSoft and some native VCV Rack objects. And of course, the audio part. So I'll have to explain that later, but I'm going to show you Ableton Live, so you can see my voice right here. And I created groups for the 3 examples that I'll be showing. And this is a track from VCV Rack. So what I'm doing right now is I'm going to send data through OSC, and this data through OSC comes from MaxMSP, will come and arrive inside VCV Rack that would produce a sound, and this will be sent to Ableton Live via audio. So I have to find workarounds for that, and it's a bit of a complication, because the OSC part, as I said, you see, is quite simple. It's just a module you install, and if you're familiar with OSC, you can easily send that through Pure Data or Max. It doesn't matter, or another OSC compatible software, and have VCV Rack produce music. So the other part, the tricky part, is sending the audio from VCV Rack to Ableton Live or your other piece of software. VCV Rack has developed a system to an internal virtual driver that you could use, but is actually deprecated. They chose not to continue developing it because there are other proposals, other pieces of software that are really nice too on your various platforms. I think the best one ever is probably Jack. There's a very famous one called Soundflower that is, historically speaking, it comes from cycling. And cycling has developed that for a long time. Now Matt Engels has made a fork of that you can find on GitHub easily. So this is the one I'll be using. There is another one called Black Hole. And Rogue Amoeba has developed another one called Loopback. I think that none of those is really satisfying, but I'm still going to use that because the problem we have right now is that Jack is no longer supported on Mac systems. This is probably because of Apple's change in policy, because of in their software policy. So this is an ongoing question. It has been an ongoing question for years now. So what I'm doing is I'm just going to send audio from VCV Rack to Ableton Live. But the main issue that I'm having is that I want to send audio from VCV Rack to Ableton Live and back from Ableton Live to VCV Rack. And this is not possible right now. You had to find several workarounds. Just a quick note about that. I've tried for this demonstration to aggregate different sound cards. I have a physical sound card, my Fireface, and a Soundflower running at the same time. I tried to aggregate both, but VCV Rack keeps on crashing. I have, buffer underruns, some drills and sounds that will get stuck. So using that between Max and Ableton Live, same thing in Reactor. Loopback only instantiates 2 outputs from your software. You cannot have multi-channel outputs. I didn't find a proper solution for that. And Black Hole only has 16 channels. I actually need more. And Soundflower seems to be the best solution because you can have 64 channels at the same time. So this is probably the best way to go. If you wanted to send, 24 channels from one software to the other, Soundflower will be the most reliable. There is one piece of software called Dante Via, where you can aggregate some pieces of hardware with the Dante protocol, which was developed by Odinate. But still, that isn't really satisfying, and VCV Rack crashes. So let's stick to that. So first example I'm going to show is a max patch. I'm going to show this to you. And in this max patch, it's a pretty simple max patch. And I've used some objects that are native to max that are called beep. And so let's unlock this. And the beep modules you can find in your in Max are actually Eurorack or Eurorack patches. They simulate Eurorack patches. So I'm going to use one of those. It's called Poisson. It's a random generator, a random pulse generator, and 2 LFOs and a lag. So the LFOs here are modulating one in another, and the lag is smoothing the signal. All of this is turned through this into OSC, into data, which is bad. That's actually really bad, but that's the best way I found. And all of this is sent to VCV rack. So the main concern I had is what happens with, is there any jitter between one software and the other? How do I clock them? Because this is when you work with softwares, you often have to think of, how am I going to clock my softwares, especially when you're working with rhythm? When you have a rhythmic proposal and rhythmic music, you need to have something steady. So here in this patch, I'm using Poisson as a clock. It's triggering every 3 seconds. And so let's listen to this. It's this click. So here you hear Max just clicking. And let's see how it works here in VCV rack. So the TroaSoft module, you need to activate. As you can see, no connection. So let's hit the config button and enable configuration. And I'm receiving in the port 7000 and receiving port 7001 and out to the port 7000. This is the OSC IP. So once I've enabled it, you can see in my scope that there are parameters. Something is modulating here, and you can see clicks. This is my click from Max. So now let's listen to the click here. There we go. You can hear a click. So every time Max is clicking, it's arriving here. And I'm going to use this tick, the small trigger here, and I'm going to split this signal to hit a resonator, very famous resonator by Audible Instruments, mutable instruments. It's a model resonator, nothing you couldn't achieve with Faust. So this Stéphane is going to talk about that, but there are many ways of making a model resonator. Well, the most famous is this one. I'm using a quanti-sympathetic string model, and I've also doubled it with an FM operator that has its own VCA and envelope. So every time the trigger arrives, it is split and goes to my resonator, and then it's also triggered once in a while. It also triggers once in a while the FM operator. And to achieve that, I use a Bernoulli gate, and Bernoulli gate is just this is named by Mutable. It's just a It's just a deterministic system where you have 50% chances to have a signal coming in and out. So when I have a trigger coming in. When your pot here is in the middle, you have 50% chances that it comes out on the left side or on the right side. Here, I want it to be more on the left side. And this is going to my gate input, triggering my FM op. So let's listen to that. So you can hear two things. First, a trigger coming in, something that is, it's strumming my model, and something is modulated. This is the other part, the modulation coming from Max here in OSC is actually modulating this parameter structure. It's a bit tricky because it changes according to the model you're using. This is specific to mutable instruments. But here what is happening is the content change. So let's do the FM up here in a while, trigger once in a while. There you heard it. Of course, they're tuned in. So, one thing, this is just a very simple patch where everything is triggered every 3 seconds. Now I'm going to introduce some chaos to make it more randomatic. And I've also patched the other Bernoulli gate module to the freeze parameter of my plateau reverb. Now let's listen to that. So every time the trigger arrives, there's a probability that it freezes, hence long tails in the sound. Oh, very long tails. Well, the music it produces is really, dramatic, sort of cinematic music. There's a reason for that, and I didn't start the introduction by that, but this is something you should, I think it's implicit, but when you use a piece of software or whatever module you're using, it implicitly implies some type of music. There is no such thing as a piece of software that it would achieve everything. Even Max has its own way of thinking, hence its own music implied with it. So every time I use an operator like FM op or a plateau reverb, the way it sounds is, some sort of cinematic way. And the thing as I will produce are always kind of dramatically cinematic, if I may say. It's a little difficult to produce pop music with that. You could, if you had a different definition of mine in pop music. So, let's stop this patch. I can hear my reverb is frozen. If I don't unfreeze it, it will continue. One of the nice things about VCV rack in this case is that what I'm doing here, I could reproduce that with my Euro rack. Because the objects I have here, I have them in my Euro rack too. The thing with Euro rack, and this is one of the main debates around Euro rack or synthesizers, is that if you wanted to start Euro rack, it's a fair amount of money to invest. I mean, every module is expensive. You couldn't have 100 oscillators just like that. You could achieve that very easily with at least rack, or if you know how to patch and you know how to program, you could do that with FOSTA without any difficulty. But still, there's one thing really nice about having a physical synthesizers is that you can play. There's the ongoing debate about whether using a synthesizer is better than using a piece of software. Well, I use both of them when I produce music, but when I play with an instrument, it stays an instrument. And instruments are, something that propose music on their own. So once you've built your own synthesizer, well, obviously it's going to narrow down the type of music you can do, of course, but it also helps you produce something. When you write a piece of software, you could do anything, but you have to choose all the time. And so I think it lacks of creativity. So this is, well, it's my opinion. This is why I have both systems working together. To get rid of all the driver problems with the Eurorack system, I invested, and there are different kind of systems, I invested in the Expert Sleepers modules, and Expert Sleepers actually are physical modules that convert ADAT or USB audio stream into CV gate, making it compatible with your Eurorack modules or your other type of modules. It could be Bushla, it could be MU systems, but these are really interesting. So it really opens the way you can work with your environment. Let's go on. So I'm going to turn off this first thing and open another one, the second VCV program. So as you can see, there are modules I already used, and this one is a bit different. So what I did here, I created 3 times the same thing. So let's have a look first at, at this. So I have the MIDI CV module resonator again, using a different model. It's a model resonator this time. Another module called segment generator, also by Audible Instruments. So I need to explain what these do. So MIDI CV is a MIDI to control voltage converter inside VCV rack. It receives any MIDI incoming MIDI, and when turning it into volt per octave, gate, or other parameters, velocity after touch, PWM, W, clock, etc., etc. But the nice thing about that is that I'm using the internal MIDI bus inside your Mac, your Apple systems. You have an internal MIDI bus called IAC bus. You could easily achieve a virtual MIDI bus with any piece of software. If you use a Max patch, it will automatically create a virtual bus. You can see it here from Max 1 and 2. If you're not using Max, you could use another piece of software like a MIDI yoke or MIDI pipe. There are numerous softwares that could help you create virtual buses, and they're all free and open source. So as you can see, I also have Millimin running, who also creates its own MIDI bus. So it's fairly easy to have a virtual MIDI bus between your softwares. What I'm doing here is I made this patch, this Max patch. Well, I didn't entirely make it. I actually forked an idea. I made this Euclidean sequencer. So Euclidean sequencer, you probably need to have a look on that on the internet for those who are not familiar with the Euclidean sequencers. But what I made here is a polyphonic Euclidean sequencer. This is a very traditional sequencer you'd find in Eurorack systems. Many developers have made those from Make Noise to 2HP to there are numerous sequencers you can find in the Eurorack world. So this one is actually a fork by Derek, who is a French programmer who made a sequencer called Zeuclide. So I forked it into a polyphonic 10-track sequencer you can find here. I will also give this freely to everyone because it's all open source. This polyphonic sequencer, let me explain how it works. Every track here will generate a note according to a division. This division, called steps, can go up to 64 steps. So from 6 steps to 64. Let's say I will divide it in 45 steps, have 14 divisions, and I'll ask him to make equal divisions in these 45 steps. And there you go. On so every slider here represents an event. This event is, every time this gray thing is going to hit the slider, it will generate the note G3, or another note that you would determine. The height determines the velocity. And I implemented this, a MIDI bus, a virtual MIDI bus, so every track can send to a different destination. So this is kind of handy. You can also shift the position of your event to come. The other thing I implemented, you can see it here. Let me close this window. This part called map is, for those who use Ableton Live, is a mapping system, obviously, but it's going to map the parameters of your sliders to whatever parameter you choose. So here I chose to map the channels 7 and 8 to L time is actually the delay time of a delay plugin. And 8 is going to this parameter here, sends B. It's the amount of auxiliary send that is going to the echo. So I'm going to automatize and the amount of info I'm sending to the delay. So let's have a look again at the sequencer. I'm going to recall the presets. There we go. And sorry, a small cut in sound. Okay. There we go. So every time Euclidean sends a track, these 3 tracks, they will arrive here in these MIDI channels in Ableton Live, and they will be sent to my 3 instances here in Rack. So let's listen to that. Let's close this, open the track, and hit play. So here you see the first one has 32 steps, the second one has 32, but the third one has 34 steps. This is why they're not in sync. So the models I'm using here, the model resonator, are tuned to sound a little bit like bells or metal pieces that are struck. And let's change the presets. Wow, that was a dramatic end. This thing you just heard, I made it for dance. Obviously, you can hear a pulse. There's something rhythmic about that, but it's off. It's really off. Well, that's polyrhythm. It's polyrhythmic stuff. Most of you are familiar with that. There are numerous ways to achieve that, but if you had to write that, I mean, write a score with that, This one is really simplistic, but if I had to show you the complete evolution of it, it's a bit complicated to write. So the nice thing about Euclidean sequencers is that you can write really complex stuff, sending the MIDI to one place. We could, of course, sample all the MIDI that is sent by Euclidean and put that in a score, and then just reproduce that with the real live instruments. So this is how we did it for a dance piece I did years ago, and having this complex structures also always evolving. With a steady pulse, you can feel the beat, but you can't predict the way it's going to fall. So that's the really interesting part, and the automation is a really nice one. The thing I also implemented and changed that from the original patch by Derek from Euclid is that you can here choose to edit your preset. You can choose your presets to be changed by MIDI. You can shift register every note, and you can listen to incoming MIDI. What does this mean? The preset here, every time I send a MIDI note, let's see that in Ableton. I'm not sure everyone can see that properly. Every time it receives C-2, it will change to preset 1. This will change to preset 2. This one will change, D-2 will change to preset 3, etc., so on and so forth. So you can dynamically change the routing. So I made an off one that initializes everything, meaning that you can write a score like that. I don't know why for this presentation it's clicking, because it's probably because of the audio stream, but in real life it doesn't. So let's listen to that again. Second one. I think you get the idea. So let's stop this. There we go. Let's turn this off. Okay. So Resonator, this module, you can see it here. I have 3 of those. In real life, that would cost a lot of money. So if you wanted to work with multiple model resonators, VCV Rack or another system like a FOST and a max patch or a PD patch would be the way to go, because in real life, having every module costs 150 or 200 euros, depending on the way it's built. And today we'll see that there are probably cheaper ways to achieve that. So if you wanted to go polyphonic, you would probably use VCV Rack. Nice thing about that is that the polyphony system is already implemented inside VCV Rack. Have a look at that. There's a Facebook page that documents that very, very, very well. So let's have a look now at the third example. No, I don't want to save. So here we go again with the same modules. Oops. So in this patch, I am using again a max patch to generate OSC. I'm using 2 resonators again, and plateau as a reverb. But what I try to achieve here is a more complex system where interaction goes from one software, Max goes to VCV Rack. VCV Rack makes the audio part, and the audio part is streamed to Ableton Live, just as a mixer. And so you're receiving this through the audio channel. But this part is the interesting one. This thing called Aeolian, DBiz. DBiz is a sequencer, is an XY sequencer. So this is a traditional sequencer you would find in your rack modules. Every time a trigger comes in here, it will shift and play the note on the left. Every time it comes here, it will shift the note and play on the right. And this one, it will shift and play the note that's upwards, and this one, it will shift and play the note that's downwards. So we don't know which one of these four is going to receive a signal. So first things first, let's turn on the configuration, enable OSC. Now it's receiving, it's ready to go. Let's open the max patch corresponding to that. Close this one, and there we go. What I did here is I actually programmed a system that will detect an amplitude. Every time an amplitude is reached, it will trigger something and then randomly distribute to the four outputs that go to VCV rack. So I didn't really program this thing. I forked this onset detection that you can find in your package manager under the US Upshot library. It's a really handy library. It's all Max MSP. So it's a very simple patch, but it's really handy for that. So I'm using here a drum loop, this famous drum loop that all Max users know. Let's listen to that, if it's all open. There you go. Everyone knows this one. Let's turn it off, turn down the volume. And let's have a look what is happening here in rack every time it sends something. I'm going to turn the volume off so you can see that Max is banging every time it reaches an amplitude, a threshold, and there it goes. You can see that the yellow button is changing from one pot to the other. Now, what if I wanted this to be in sync with some video? Nice thing about OSC is that I can send that to Millimine too. Millimine is a software that generates video. So here you can see I have found some images on the internet, and it shifts every time, not every time. I'll explain why. It shifts in sync when there's a bang coming. And now let's listen to the audio part. So as you can hear, let's turn this off. You hear it's always the same notes. Why is it? Because it's always shifting inside this reservoir of notes that are tuned to according to a certain scale. And this is the interesting part, where every threshold is just going to choose randomly inside a reservoir, hence making some melodic things. So this is also a thing I used in dance, where you need to have a certain melodic structure. You don't need to, but we chose to. So let's have a look at the max patch again. Turn off the drum loop. What if I used a pulse generator again? This is the other part. And I'm going to use the pulse generator again, but this time I'm going to hook up 4 of those. And this pulse generator, oh, by the way, this pulse generator isn't Max stuff. It actually comes from SoundHack, and the developer who developed that in the Beep library, if you have a look at the help file, he gives every information. It's just a basic random and chaotic piece of program he did on SoundHack. So Super Collider. It's Super Collider stuff ported to Max. I think it's even Gen. So this Poisson thing, pulse generator, is I turned off the chaos, and I looped the output of to 3 other instances of Poisson. This means that this is the master clock, and the 3 others are actually tuned to be subdivisions in time, I'm still doing polyphonic polyrhythm here. So let's have a look at that and change to my pulse generator system. So you can see it flashing here. And let's listen to that. Like a illumine. Well, if we're here that I use that trigger audio and video, it's kind of related to a sound. You could, of course, put an input here and have the onset detection detects incoming signal from an instrument, and then make it generate sound inside VCV rack and go to Millumin at the same time. This is how I would set up my system. Set up a system to have a complex audio and video stream at the same time. Could write a piece out of that. But what I did here with a steady pulse sounds a bit like minimalistic music, I'd say. Minimalistic music like some Reich or music, but there's no repetition inside. The only thing that is repeated is the harmonic scale. So let's continue. So I'm turning off the pulse. As I said, you can have a microphone coming in. What if this microphone was my voice? Let's see if it works. I have an input here, and I've hooked it up to my onset detection. So now it should be triggering. Is it? Yes, it's working. And you can lower the detection. As you can see, every time my voice reaches the threshold, it will trigger a note here and an image. The images are not always triggered. There's a reason for that. This object here is a shift register. You can find a sequential switch, You will find that in VCV rack. It actually switches the inputs to the output. So if there's no sound, if there's no input, then there's silence. This is a way to avoid a continuous stream of audio running all the time. This is one of the major issues you would have with synthesizers turned on. They keep on generating sound. So this is my way of creating silence. There are others, but this one is nice. And there we go. So this is probably I'd say the neatest way I found to hook up some complex systems between different softwares would be OSC, even though I still believe that OSC has its own issues and it's not the best way to work. What I'm really missing now is a real programmable patch bay, something that you would choose between different softwares. Say I have a software that has 16 outputs, another that has 4, and have them all being merged inside a piece of software, but I could choose to split them, merge them, and send them to other softwares. This would be really nice and convenient. This is what Jack does in a way, but because Jack can't add signals together. It can only split them. But what would be nice is sort of mixer, patch bay. In the Eurorack world, we would call that a unity mixer or a multiplier. Basically, these are just the systems that we would use. But right now, there is no steady way to make that. I'm not sure if you guys or guys and girls have a way to achieve that. I found several workarounds, but they don't seem to fit the purposes we're needing. The MIDI system is really going to be here for a long time, as I said, particularly since Ableton has implemented that inside Live 11, and this piece of DAW is a very famous one, so lots of people use it. I'm not sure it's a good thing, but things are going to change accordingly. These past 15 years, lots of things have changed in the audio domain. So why not dream of a huge control voltage, let's not call that control voltage, but audio stream that we could reroute wherever we wanted to. As we said, it's easily mappable to a piece of hardware like Expert Sleepers or another piece of hardware. You could easily turn that into a control for external gear. The tricky part about that is it's always a one-to-one signal when you send CV. So, but it makes it easier to understand. So I would go CV all the way if I could inside my softwares as well. So I think I'm a bit in advance with the timing. I don't know if Jan is back there. Probably. Mm. Mm. Yeah. Well, I must admit that most of the time it's when you program your things, you try to make something that you know very well, because there's one thing on stage is a certain situation, and producing music for others or for yourself to make a tape music is completely different. So on stage, why is it different? Because there's an audience. When there's an audience, you always lose your you lose your concentration. I mean, 90% of my concentration just vanishes. So I need to have a piece of software and gear that I know well. This is why it's interesting to have a synthesizers, because I can rely on it. I know what's happening here. I make very little mistakes with it. As if I was programming, I can do lots of mistakes. And let's say that the huge amount of possibilities. Yeah, as you probably saw when I right-clicked on VCV Rack, I have like thousands of modules. How can I choose? I have to experiment with them. So it's a complete different thing. Doing things live, you need to rely on something you know, And because your goal is not to explore, your goal is to make music live for people. So sometimes it's interesting, but the nice thing about Eurorack, an instrument, is a hazard. I mean, chance that something new can occur and you can react to it. And you know how to react with it. If you do that with the software, if you're experimenting, sometimes it goes wild and you don't know how to get out of it. You're just stuck with it and you need to figure a way. Sometimes it crashes also. That's hopefully for this demonstration, nothing crashed, but I had numerous crashes trying to build up this presentation, and even having the audio stream go to you guys with 4 different softwares running at the same time. I can't tell you my CPU is really peaking right now. It's so this means I can't, with a brand new MacBook, I can't really rely on it. So nice thing is having another piece of instrument working on that side, producing music. I would get rid of VC Rack and do that with my Eurorack. That will sort of clear my mind and be really assured that I have something running, you know. Because for you guys who are familiar with the Max MSP world and programming, as I've been doing this for the past 20 years now, we've had so many crashes live with the audience that is not, I mean, that is, we can't do that anymore. It's done. We have to stop that. That is not music. We have to find a way to be sure that something musical is producing. That's my opinion. I do music for people and I do music. I don't do research. Research is one part when you work, but at a certain point, you need to have a steady and solid programming stuff so you can present it. Even though it's still experimental, sometimes you have pieces 90% experimental stuff and crashes. I had, unfortunately, numerous experiences with that. And you always have the feeling of it's a failure in a way. I'm not sure if I'm clear for that, but I'm. So the protocols here, I sort of, I think everything relies on that because the software, you know them, but the way you communicate with them is the tricky part, and this is the part that crashes all the time. Not to mention if you had a huge stream of OSC running from sensors to your patches, it almost always overloads your machine. This is a very famous thing. So you need to narrow this down. It's a very refined thing to find, I think. I see that. We have to switch to Rust to avoid part of the crashes, says Stefan. Yes, we do. The funny thing I have to share with you guys, because for this presentation, I was thinking of showing you something I've been trying to work on. I'm not the only one, but I generated with Euclidean, as you saw, some notes that are sent to VCV Rack. What I did is I recorded the notes, the control voltages, frequencies, and the gates. I recorded them into an audio, a buffer. And this audio buffer, I just used that and tried to use that as a new control source. I've put that in one of my modules called Morphogene, and the Morphogene, I tried to use that to remote other pieces of my modules. The thing is that with the 1 volt per octave convention in the Eurorack world, we have a problem. It doesn't, the audio isn't, it will clip when you're trying to use control voltage for pitch. What happens is that the pitch, when it reaches the volts above 1, it will clip. So, but you need 5 volts to control pitch. I'm not sure if I'm clear right now. The other guys are probably better on that part than me. But so I tried that on a cassette player. I recorded control voltage and gates on an analog cassette player. And that is so much fun because you can let's say you record a loop with a sequence, have it turn it around. What if you could slow this down and you could make it faster or slower? You would, of course, everything would detune, and you would slow down the speed of your sequence. And this is what I did, and it's so much fun to do. I tried to do that with the morphogene, but in the digital world, it doesn't work at all. You had to oversample everything. I'm not sure if I'm clear, but
so apparently I'm not here on the YouTube stream. Sorry for that. There are some question marks for you on the. Okay.
Have you found ways to get VCVRAC out of software and into hardware with something like an Arduino Raspberry Pi? Oh, that's a very interesting. So I haven't found pieces. I haven't found solutions for that. But if you continue, if you keep on, Brandon, if you keep on looking at the stream to today, I think I don't know when they are, when we'll see that afterwards. Sorry, just. There we go. Afterwards, we're going to see that on a Teensy, if I'm correct, right? So Teensy is probably a solution. On a Raspberry Pi, that would be kind of easy because you could easily make a PD patch, a pure data patch, and yeah, Roland is going to speak about the Teensy world, so he's going to probably show you how to program that on an even simpler piece of hardware. But with the Raspberry Pi, you could do that with pure data. The other tricky part would have to need to have a proper ADDA converter, and I'm not sure the Raspberry Pi is really good with that thing. I don't have much experience with that. I think recent audio interfaces let you use audio outputs as CV outputs, and not all of them. Unfortunately, most audio outputs actually filter out CV because control voltage is bad for a sound engineer. As a sound engineer, I can tell you that. We usually filter that out because it just blows your PA. It's very dangerous stuff. It's continuous signal is the worst thing you can have. And a lot of modules exist as hardware modules, of course. Yeah, that's right. Roland will speak about that. I mean, he's the guy for that question. No, the reason I use expert sleepers is pretty simple. Actually, I have to be honest with you guys. Most of the time when I go on a gig, I have my Fireface 802 hooked up to an ADAT system, and the secondary ports of the ADATs on the Fireface, because there are 2 inputs and 2 outputs, secondary port is used for the modular. So the ADAT is completely DC compatible. So I have my module that's completely integrated with absolutely no delay between Max MSP, Ableton Live, or whatever I'm using, and the mixer for the PAs. So this is why I'm using expert sleepers, and the converters are really good quality converters because I also use them as input and output not only for control but also for sound. If I have a microphone running in my modular, I could send that to my computer without using my Fireface. So it's really handy for that part, though it's kind of expensive though.
Okay, so thank you very much, Max. I don't know if we can applaud you, but I can try.
Thanks, guys.
So the next talk will be by Making Sound Machines, which is a duo of artists and makers from Düsseldorf. Making Sound Machine is composed by Enrika Giesel and Roland Nebe, and they build kits, modules, and do-it-yourself projects as well as their own circuitry, and use the project that they build to make music. Enrika studied audio engineering in Düsseldorf and holds a master's degree in electronic engineering. She develops music hardware as a day job and tinkers with her own designs by night. And Roland is an artist, musician, and composer also from Düsseldorf with an academic background as a classical performer and media producer, working with Auska, Volker Bertelmann. He has contributed to numerous motion picture soundtracks, including the Academy Award-nominated score for Lion. Together with Andreas Huck, he runs Warp Type, a group of graphic moving image makers creating live visual and producing artistic video content for symphonic orchestra, classical ensemble, and composers all over Europe. And they will talk about and guide us through building a simple prototype polysynth with Faust DSP, Arduino, Teensy 4.0, and modular. So, Enrica and Roland, it's up to you.
Hey, hello.
Hey, good morning.
So yeah, first of all, good morning to all of you. We have the croissant ready. We have the coffee ready. The first question of all would be, can you hear us? If anybody could just quickly type that in chat that it works.
Ah, nice.
Okay, thumbs up
here.
And the other thing, maybe Enrica, you can play a note on the hardware real quick.
Yeah.
Are you hearing that as well? All right, thumbs
Perfect.
up all around. So everybody watching this after the fact, this was a live stream. Everything that happens. You know how it is. And this is also, of course, part of the Programmable Audio Workshop 2020 whole day. And yeah. What is this all about? We are, first of all, Roland and Enrica, we got introduced already. We're a couple of makers and making kits and DIY projects, and also making our own hardware. And we're using some of them as what building today. And so some people videos with Faust running on a Teensy 4.0, Teensy 4.0, and yeah, we're running Faust on it. We have a Teensy 4 that receives MIDI via USB. The Teensy runs Faust code, producing the audio. We have a computer that sends MIDI via USB, and that acts as a relay, basically. And the MIDI that we play comes from a simple MIDI controller. Let me play you one of the videos real quick so you know how it sounds in a more musical context.
We don't hear sound, I guess.
Ah, wir hören.
The sound of the instrument is not working for us.
Yeah, we are checking. Ist das mute? Ist die Quelle mute?
Okay. Yeah, I'm sorry about that. We're just gonna skip the video part for now. I think it's on our YouTube channel if you want to hear it with sound. Sorry. Let's go to the cam instead, and maybe you can play some chords on it. Yeah, so this is all generated on the Teensy, and it's all made in Faust code. So it's a very simple polyphonic synthesizer, but it's already just something that spawns in code and runs on hardware. So and I think the big idea here is I think everybody that wants to do something in hardware in the end has to tackle like 3 problems. They need to be a musician, of course, to have the musical idea what they want to do. They need to be a software coder, so they can write the program, and they also need some skills in putting together the hardware. And so each of these things has become a lot easier in this combination. And while we know that this is not a finished thing in the end or a finished module in the end, it's a really, really good start to get into it. So let us walk you through what you need to actually build it. And we're starting, of course, with the Teensy 4.0. And yeah, we have one in hand right here. It's a really small microcontroller dev board with a really fast CPU, so you can, or MCU, you can run it at 1 gigahertz, I think. No, at 1 megahertz. So it's really, yeah, it's really a fast core. Then the next thing you need is the Teensy Audio Shield. So that's a small board that has the codec on it, and it runs basically what it does. The Teensy generates the digital audio, and then the codec translates that to an actual audio output. And this is one of the things we talked about before. So this is a really good converter, and you can get good audio quality out of it. So you need that board. So the next part you need are stacking headers. Let me zoom in on these again. Here they are. And can you show real quick how they go into the board?
Yeah, so we have a basic way of putting together a sandwich. We have the headers like this, and then we can put this into a breadboard, as you can see here. Yes.
Okay, so the next thing you need is basically the same thing, but with pin headers on top and on the bottom.
Yeah, and we put them in the Teensy like this, solder them on, of course, from the other side, and then can we can have every pin outbreaked as well to put in some potentiometers or sensors or other stuff.
All right, so the next thing we'll need are jumper wires like that. So basically those connect on top of the pin headers. So you can, the pin headers you don't need for connecting the audio shield, you can use for other stuff like reading inputs and outputs. Yeah, there's some handy ways to do that as well, which we're going to show. Maybe just stack up that thing real quick, and let's have a look at how that's will work. Yeah, so there's the audio shield. In between goes the Teensy. And then attach like those jumper wires on top.
Yeah, they basically go on top. Or break out the left and right channel from the audio shield.
Yeah, you actually need to solder this, of course. We would workshop, but and we've like the whole thing ready.
And for breaking out the left hand. Here are some where you can put all your make with jumper wires.
Yeah, so the audio shield either comes with the headphone output, which is not so practical for your regular dealing with. So in the end, need the same audio. So we would always just break out the actual those, and for this you basically pins slotted together, and you can get them in the variety basically. And a really cool thing though that we want to show you, this is a mutant project as well, and she these mutable breadboard friends, and the breadboard friends are little circuits that slot to breadboards.
Yeah, you can see it plugged in over here already. Here we have one not plugged in, and it holds 4 jacks to, and yeah, tip and switch of those jacks are available via these pins, and so it's very handy to plug in a jumper cable to connect.
Yeah. So instead of building the circuit on a breadboard, you would just plug in this pre-made PCB with 4 jacks already on it. Or there's other variants as well that have potentiometers. We have that just has 4 pots and a lot of jumpers. And every build with pin header, you can just plug in, and we kind of really like this idea, and we started building our own sort of sub-circuits with that. For example, these are filters where you would just go and connect to the pin header, and then you would go have basically a test ready on a PC to the image. So you can prototype really rapidly.
Like Legos.
Yeah, hang on. So I want to show. Of course, these connectors, Donkey Kong. We just wanted to, because they're one part. They're basically the connectors to hook up the patch cables, and they have a switch. So a really cool thing is that you can unhook. You can unhook your circuit if no cable is connected. So you can get rid of a lot of ground harm that way, just because of unpatching the inputs physically in circuit when no cable is attached. That would be really convoluted explaining it, but great. You can get that with a great DIY store. And so the last obvious part here is, of course, a MIDI controller. We're using today an Akai MPK Mini, which is one of the cheap ones, but that has already everything you would need. It has note inputs. It has controller CCs, and it has some pads to play notes. And so this already has a lot for little money.
And the nice thing is it has 8 jacks. 8 knobs. So you get like 8 parameters you can control.
Yeah, basically, and that also brings us already to one thing that's really, really different in hardware as opposed to software, is whatever you do, you will run out of knobs, right? I mean, you will have 8 knobs that control 8 parameters, and you have to find a way to sort of deal with that. And so in the way, like these MIDI controllers, really nice because they constantly remind you of, oh, if that parameter is not so important, maybe leave it out, or maybe lump it in with another parameter and make them interconnected. So we're going to talk about that later. And so the other one we wanted to talk about real quick, so this is a little higher end, but the cool thing about that is it doesn't only have, it's a Arturia KeyStep Pro, and this one doesn't only have MIDI, but also control voltage outputs. So that lets you hook into the modular world a lot quicker, because you won't only get the MIDI output, but you will also get voltage outputs, and done in a quite intuitive way and still comparable to sequencers that are in the Eurorack. It's still comparatively cheap. I mean, like Eurorack sequencers can get complex real quick and are produced in really small numbers, and then they start to get really expensive.
Yeah.
So this might be, if you want to splurge, this is a nice one. And so yeah, the next thing we want to talk
software.
Yeah, the software and how the architecture, basically, how are we building it?
Yes. So do we want to first show the software bits, or?
No, just...
Okay, yeah. So how are we building it? So basically the heart is built in Faust. There we are building a simple oscillator, which we will show later how we build it. And in Arduino, we are then using multiples of this one oscillator for the polyphony. And also we are reading pitch and gate from the MIDI controller and setting envelopes for the Faust oscillator, like ADSR, with our MIDI CC commands. And then we are mixing all those oscillators together to one stereo output. And that is done by the Teensy audio library. Yeah, so that was like the software part. And in hardware, we are using MIDI. The MIDI is generated with our little keyboard, and we are hooking it up to a PC. And also we are hooking up our Teensy as a MIDI device to a PC. And at the moment we are using MIDI OX for patching it together. But you could basically also use a DAW or some other MIDI loop program, basically.
Yeah. So again, if you play some notes.
Yes. So I don't know if you can see it. This is the MIDI OX on the screen. Okay, I don't think we can see it. Okay.
Yeah, but what you can see there is that the MIDI notes are relayed via the computer. And so the Teensy actually offers you pins on the underside to make it a USB host as well. And that would probably be the next step that you wanted to take, to just make it a USB host. But then on the other side, it's really, really nice to have the computer to have a quick look whether the messages you're sending are actually the messages you wanted to send. And it's a nice control step between. And honestly, for the whole development part, you have the computer there anyways. But of course, there are a lot of steps you could then take to make it more of a standalone thing. So and basically making it a MIDI host, making the Teensy a MIDI host would be one of those things. If you don't want to go that route, you could also go ahead and make a hardware MIDI connector that uses the UART port. And the code for that would be quite similar as to what we show right now. So one really quick thing, we published all the code. So if you want to follow along after the fact, hang on a real quick.
Yeah, you can see the GitHub link.
You could go to our GitHub. It's github.com making sound machines, and the repository is the only one in there at the moment. It's Faust on Teensy. And we made 2 directories. One is additive synth _Faust. This contains the DSP code. And we went, we went through it and commented in a lot of things. So if you have any questions about how that works, it's in there, and we're going to explain it, of course, as well. And then we have the Teensy code, which is already the generated code from Faust thrown in with the Arduino code. So this, if you install the stuff that we're going to talk about later, will hopefully just compile and upload to the Teensy Arduino. And yeah, I mean, GitHub, if you don't know it, you can just download the code as a zip from here. And so the very first thing we would show you is how the Faust DSP code that's sitting here will look in the Faust IDE. And so, yeah, I mean, I guess most of you know this one. This is the online version of the Faust IDE, and it's available at faustide.gram.fr. And because we noticed that in previous talks, it was really, really hard to actually see the code, we put that code on slides for you. So, but first things first, here's what we're trying to achieve. We're building in Faust, we're building a really simple voice. So this will become one voice in our polyphonic patch in Arduino. So as you can see, it's parallel processing 8 different partial harmonics, but this is going to be one voice. So we're going to have this 8 times in the end. And the Teensy will, in the end, run 8x8 of these harmonics, so 64 harmonics. Yeah, this is something we pulled from the Bela examples. So there's not that many examples for Teensy, but the Bela examples are really, really nice. And if you take our code and substitute the Faust code for some of the other examples, you will be able to run really nice stuff on the Teensy as well. Of course, there are some memory constraints. The Bela is based on the Beagle board and it has a lot more power, but it's also a lot more expensive. So I think it's a great trade-off. Faust IDE I showed you already. That sits at faustide.gram.fr. And it's really, really nice. You can run the code in your browser and just see.
Yeah, you can see beforehand if it breaks or if it makes the sound you imagined to make. So that's very nice.
Yeah, so that's really cool. And what you need to do is you need to paste the DSP code into the window there and then give it a name. We called it faustadditive.dsp. And you just have to keep in mind that the name you put in there, you want to name this nicely because you're going to need it later if you want to integrate it into Arduino then. Yeah, so the first thing here is the Faust code oscillator.
Yes, so
yeah, so the thing is here, we lowered the resolution of the sine oscillator in order to make the computation easier on the Teensy MCU. So for that, you use read table, and then you basically just reduce the table size by 1 bit. Yeah, that actually makes the code a lot slimmer. And as we're running, yeah, like we said, as we're running a lot of sine waves there, this is a good compromise to just deal with it with more efficiency. Then the next thing here is setting up a user interface for gate, frequency, and gain. And one thing to note right here is that, okay, so you have the blue variables. They are the variables you use inside Faust. And you have the orange variables. These are the variables you will going to see later in Arduino. So it's your choice if you call them the same or call them differently. We figured out for us it's easier to call them the same thing because you don't get confused what you're actually doing. And yeah, so just remember blue variables are inside Faust, and the names of the user interface objects, which are in orange, that's what you're actually talking to in Arduino then. The other thing you can see here is that you set the default values here. For example, for the frequency, the default value is 440. And then you set the limits of the frequencies, so which the lower limit is 20 hertz and the upper limit is 20K. And you just have to keep them in mind because, of course, in Arduino, you could set things outside those limits, and then you might run into troubles of just stuff not behaving the way you wanted. We didn't have any bad crashes, but you're just going to have stuff like nodes ringing too long, or I don't know, frequencies clipping at the top range or something like that.
Yeah, or the knob has a strange range.
Yeah, so just keep that in mind. You're setting the limits of your DSP code already here, like the nominal limits you want to achieve. So the next thing we implemented here is a filter, and I know that is uncommon for additive synthesis because you don't usually do that. But we figured out that it's really, really fun to play, and it makes it can carve out the harmonic resonances really, really well. Maybe you want to.
Yeah, and also we use using a resonant low pass, and the resonances are very fun to play with. So
yeah, maybe you want to play a couple of notes. And if you sweep through the macro. Yeah, you almost get like Formanty type sounds out of that, and I think that's also a nice point about making hardware modules. Apart from the theory that's behind the instruments, you also have to find stuff that's fun to tweak and fun to play in the end. So, and that gives you a little bit more freedom and opportunity to carve out the sound. So then the next piece of code here is the harmonic oscillator. And this is really interesting part of code because it uses an iterator range that is triggered later with PAR. PAR does parallel processing. I can show you that in the main function in the end. And so what range does, it just creates instances of the user interface for the ADSR for each of the partials. So we're going to create 8 partials. Each of the 8 partials has the ADSR in the end. You will get a user interface for the volume for each of the partials. And in the Faust UI, they're represented as sliders. So if you hit run in the Faust IDE, you can already play with those. Arduino doesn't care if you have a slider or a number entry or whichever of the user interface types. So you can just choose the one that you like best for that here. And the other thing that's interesting here is that the parameters are smoothed, so you don't get steppy response from your knob inputs in the end. So then at the end of this code is the process part, and this is where the whole code comes together. You parse with parallel. You parse through 8 instances of the harmonic oscillator. You combine them all together, and then you run them through the resonant low-pass filter, and that's basically our patch here. So again, here's which parameters we will have in the end in Arduino. We will have the gate, frequency, and gain, and they set the fundamental pitch of the harmonic oscillators, while all the other partials are whole number dividers, no, whole number multipliers, so ×2, ×3, ×4, and so on. We will get the gate, the node on or off. We will get the gain, which is the overall volume. We will get the filter frequency and filter quality. We will then get the filter makeup gain, which is just something you can play with to counter like peaks and also the drop-off in perceived volume. And then the fun part here is with this percent range iterator. Faust makes you a user interface for all 8 instances starting with 0. You get volume 0, volume 1, volume 2, and so on up to volume 7. And these are for one instance of the generator. These are, the individual volumes per sine wave, basically. So here's where you can really play with the harmonic oscillator. And you can also get the same thing for the ADSR. So you can set each of these ADSRs per sine wave separately. So just note that in the end, we will also have to set for 64 sine waves, we will also have to set 64 parameters. So you will see in the Arduino code, just to keep things easy to read, there's a lot of granny coding where like blocks of code are duplicated and copy pasted just to image or just to mirror that you're setting the 7 parameters here and done. I think that sometimes help if you look at it. And then, of course, last step you will need to do in Faust is you need to export the code. And for that, you get you make sure you have selected your project here, the correct DSP, and then you hit the little truck, and the export should be set to Teensy and Teensy as architecture. If you hit compile, you will get the download button. And once you downloaded everything, you will get the binary.zip, which actually doesn't contain a binary, but contains a text file C++ and a header file for that. And these two you drop in the same location as you would set up your Arduino project, which is, if you look at the GitHub, that's what we already did for you here.
Yeah, it's the same folder. So we have a folder named like your Arduino sketch. Then you have the .eno, and in there you also have the C++ and header file.
Yeah, so these actually just go into the folder, which is really cool. So that's really great integration, and it's really quick. And so where are we here? So now we're basically done with the Faust part.
And next we would show how to set up all the parameters in Arduino.
Yeah, so first things first, what you need is you need to install the Arduino IDE. It lives at arduino.cc. It's a simple install. Then you need to install the Teensy libraries. Those you can get at Paul Stoffrigen's website. That's the guy who makes the Teensys and designs them, and also offers a lot of code. So it's a really nice site. Sift through there, see what you can find in terms of libraries that are already pre-made for Teensy. It's great stuff and really well prepared, and good examples too. And then there's one special thing that you need to do. You need to go to the Arduino folder, your Arduino install, and you need to change the linker for Teensy 3.6, 4.0, and if you have one 4.1, from GCC to G++, just in order to for the Faust thing to compile and link into the project correctly. And there's a much better explanation for that at this URL at faustdoc.gram.fr. And there's tutorials about the Teensy, and then there's this special note about the Teensy 3.6. Let me show you that real quick. The page looks like that. And there's a description what you need to change in order for that to compile. And I know this has been a little stumbling block for just people trying this out, so make sure you do that. Otherwise, your code won't compile. And so the first thing we would look at here is the overview, basically, of what we're trying to achieve. This is not really code, but this is basically a quick, dirty overview of what we need to do in the code, so just that you know what we're talking about next. So the first bit is we want to import the audio shield, and we want to import the code from Faust. We want to then create 8 instances of the Faust harmonic oscillator, and we want to group them together, n and n plus 4, so voices 0 plus 4, 1 plus 5, 2 plus 6, and 3 plus 7 make up one voice, and that's so we get this nice detuned analogish sound. Do you want to play a couple of notes?
Yes.
So there you can hear you have this nice chorusy thing, and that's because we use two harmonic oscillators per voice, basically, and they're slightly detuned like they would be on an analog synthesizer, and so you get a much less static sound. And that's a theme you will also hear throughout this talk, that we try to sort of break up a little bit the stability of the sound by detuning things, and also giving a little bit of leeway to the parameters. And there are already easy ways to do that. Then what we want to do is audio library stuff. So this hooks into Paul's code. We want to use the Faust harmonic oscillators and route them to the individual left and right channels. I'll show you in a second how that works. We will want to set up MIDI to note frequency conversion, or MIDI note to frequency conversion, which what that means is I'll also show you later. And we want to set up the polyphony. And then comes the setup loop in that, or setup function in that we want to just set the mixer gains, enable the audio shield, define the handles for the USB MIDI callbacks. So this is really good functionality, because in the loop, then you just say you want to read the USB MIDI. And what that does is the loop is basically free, or and the audio processing is done the whole time, but inputs are only processed if a MIDI note comes in. So what you want to do there is catch the incoming events, and then you got the handles, the MIDI note on, MIDI note off, and control change. These take the three variables that MIDI provides you with: the channel, the note, and the velocity. And you catch gate on or gate off there. You catch the pitch, and you want to handle the voice allocation there, just so that you don't run into problems with how many notes are pressed, and if somebody's pressing the same note over and over again. And so you need a bit of code for that. And then the most interesting thing are the control changes. We have 8 CCs here, and we set 1 to the volume of the fundamental, and there's a nice trick to that as well. We set the next CC. We do a macro. We set the volume C0 to 7. In CC3 and CC4, we do the center frequency filter, and the 7, the sustain, and 8, the release of the ADSR. So let's just look at the code real quick, how that works. You include the audio library. You include Faust additive.h. This is the header file from the Faust export. Then you instantiate just the I2S and the chip itself that's on the audio shield. So that's code that just gets those two running. And then comes the interesting part about the Faust integration. What you do here is you make 8 instances of Faust additive, and Faust additive again is the DSP code that we got from Faust, and you just give them variable names. So we just call them additive synth 0, 1, 2, 3, 4, 5, 6, 7. And again, what we want to do in the architecture is combine 0 and 4, 1 and 5, 2 and 6, and 3 and 7. So here is the mixer stuff. This one really cool thing is you can actually go to a graphic user interface tool at Paul Stoffagen's site. It's pjrc.com/teensy/GUI. And there you can generate basically this sort of patch for you. And this is already very familiar for people who are into modular synthesis. What you do is you create mixer objects, and then you hook up the ins and the outs. And I've pasted a little screenshot here. Basically, we mix the additive synth 0 to 3 together in a mixer of 4, then 4 to 7 in a mixer, and then we need to recombine them. So the Teensy mixers always have 4 inputs and 1 output. So what we are doing here is once for the left channel and once for the right channel, we're combining the inputs and sending them to the left and the right channel. And yeah, I mean, this is a bit tedious stuff in the code in the end, and it's a lot longer here. So whenever you see the dots in our pasted graphic here, just know that there's a lot more of the same code basically there. But the gist is make mixers, make patch codes that connect a mixer in and a mixer out. And then it results in the signal flow that you see on the right here. So the next thing that is set up here is the node number to frequency. It's an array that just tells all the 127 MIDI node numbers which frequency actually corresponds to which node number. And it's the, yeah, I don't know, it's node number 0, C0 is 8.18 hertz. That's how you read that. We commented the node names above that, so you can actually check for accuracy. You can add decimal points if you want it more accurate. And so here's the first real neat trick. We make a function to set the ADSR. And so we have control over each ADSR for each of the harmonics, which is really, really cool. And so that does mean we don't need to set them the same value, right? So what we do here is we get the value that's going to be the 127 from the CC. And then we do some math here, which is explained on top. But what we want to do is convert it to a floating point value between 0 and 1. And what we then do is add a scalar, just a multiplier to some of the values. So what happens here is for the fundamental, the attack is the longest. So the fundamental needs to, the fundamental comes in the slowest fashion, and then the highest harmonic comes in really quickly. Maybe you can again play single notes. So what you can hear here is that you can actually get a timbre change just over the attack, which is really, really cool. So that makes it lively again. We do the same thing for the decay, just the other way around, so it evens out before the sustain. And yeah, the way you set the parameter values is then just by addressing the FOST instance, FOST additive synth O dot set param value, and then you address the value we discussed earlier, which is DK0 to DK7, and then you give it a value. Then there's the sustain values. We keep them at the same level because the thing with the overall values we already did in the mixer. And for the release, we again do the same thing. So, okay, so the next thing I want to talk about, and that's a really, really cool concept, is having macro knobs. And what that does is you want to set the whole timbre of the harmonic oscillator at once, but you don't have a slider or knob to set each of the volumes, each of the 8 volumes individually then. So instead what you could do is to map those onto a single knob that goes from 0 to 127, and then, for example, make harmonic 1 loud in the beginning and soft or off in the end. But harmonic 2 do the inverse, be soft in the beginning and loud in the end. And harmonic 3 starting soft, then going loud, then going soft again. And then more variations of that, as you can see in the graphic here. The higher you go in this graph. And what happens there is that you get different combinations of timbres as you move along the knob. And is of and so about the value and the mean callback we're seeing so stored node -1 means the node is off, so we're looking for the first instance in the array of 4 nodes that is -1. Then we're setting that array to setting that to the node, so we know, okay, well, node 1 is C0, and then we're assigning one voice to each of those numbers in the array, basically. So voice 0, you can read it as voice 0 has synth 0 and synth 4 assigned. Voice 1 has synth 1 and synth 5 assigned, and so on. And so this is basically polyphony code. And again, here you do that on my node off. You just switch those off again. If you find that the node off is the same as one of the nodes that's already in the array, then you switch it off and set it to 0. And then the most interesting part here probably is the my control change. It goes through the cases CC1, CC2, CC3, CC4, and so on as part of the and you set something to be right out of function. For example, the volume on it. And then there's also in this just going to the set marble, catch the value. And put it in the function. And so this is the code in Arduino. We need then to flash the code onto the Teensy. We need to connect the Teensy with a USB cable. Be sure to make it with a data cable. We need to connect the Teensy 4.0, and we set it to 816, which is a little overclock already, but runs really smoothly and doesn't get hot. We need USB type serial plus MIDI, and then we use the arrow to compile and upload. Let me show that real quick here. You just go here, and then you have either compile or upload. You hit the compile, it goes through a whole deal and starts compiling that, and then you can upload it to your Teensy, which we've already done, of course. So what is happening then is you can combine the whole thing with modular.
Yeah, so I think our time is almost up, but we have a little patch which we would play real quick for a minute or so, right?
Yeah.
Yeah, so this is again the like try sound. And now I will patch it in some modules for basically effects.
Yeah, so what we're hearing now is running that into an amp, and then we use mutable instrument streams as a VCA. We use this not rocket science wobbler to make the nice wobbly sounds. And we use the Plinky, which is great DIY project, to add the cool reverb. And so that's it from us. Maybe we have some time for questions, but if we don't, then let us know.
No, sure, we have time for questions. And thank you very much, Enrique and Roland, for this very nice and very close to what we would have done if we were not in this special configuration that is a hands-on workshop. And so with all the camera, etc., I think we have all the information to redo that by ourselves. That was really, really nice. So we have time for questions. Do we have questions on the chat, or if you want to speak, please unmute your mic and speak and ask your question directly.
Let's see.
Okay, then I will start with one question about this set volume macro. How this, I think it's, as you explain, as soon as you are using real hardware, you run out of knobs very quickly. And so this is a way to control multiple parameters with just one knob. How the idea came from, and how effective is it? How easy is it to use?
The thing is, actually a lot of modules in Eurorack do that.
Okay.
A lot of the DSP-based modules, especially, of course, because you always end up with code that has a lot of parameters you can set, and you just need to choose a user interface in the end that produces a nice result. And I think there's already a choice in there, very much like what Max said in his talk, that you're building an instrument and it will be tilted towards a certain use. So, for example, here we thought, okay, you want to control the volume of the fundamental, because that's really a part of how weighty the sound is. But then you want to control the timbre maybe as a whole. For example, on a hardware knob, depending on the resolution, you would have much more resolution. For example, 4096 steps, and then you could fine-tune that a lot more. But the overall idea that you group together that you group together parameters is really nice, because it also lets you play the instrument in a different way. There's some great examples of grouping attack and decay, or attack and release together on macronobs as well. And you just start to set the envelopes differently as you would an ADSR envelope. So if we introduce 2 more parameters here, we have to, of course, give up 2 knobs of the ADSR, for example, and then you would just think of a nice way to still be able to use the parameters in a good way. Does that somehow answer the question?
Sure. No, that's really nice. There are other ways to control multiple parameters. For example, I don't know if Thierry, are you still here? Thierry Caron? Okay. We did a software with Thierry many years ago where which was inspired itself by a software developed at GRM. And the idea is that you represent all your slider or knob on a 2D surface, and the value of the knob is the distance between, so you place all the knobs on this 2D surface, and the value of the knob is the distance between the place of the knob and the center of a cross that represents the center. And then, so you can move a slider close to the center or far from the center to change the value, but then you can move the center itself and change all the slider at the same time. So basically you do a two-dimension projection of a n-dimension space, and you can change the projection by moving the knobs, the sliders, but you can explore the projection by moving the center itself. So that's something that can be done with a joystick, for example. So that's a really interesting questions, I guess.
Yeah, that sounds great, and that's I think something that can be explored nicely in Rec, because there are a lot of so for example, if you would imagine the knobs as CV inputs, which we didn't have the time to show like the circuitry behind it. If we wanted to show the circuitry behind building a whole module, then it would probably be like 10 of those workshops.
Sure.
Yeah.
But there are then, of course, modules that just do user interface. So there are modules that do joystick. So if you basically this matrix or XY axis projection that you talked about, that you could potentially do by hooking up a joystick module and plugging in
a CV input.
In a CV input. And
or
then,
multiple CV inputs.
Then you would possibly get that plus the macro knobs. So, you know, so I think it's really nice in Eurorack or in modular, you can sort of choose your control paradigm separately from the module itself.
I have a question on the cost of all the stuff that we can see here, and in particular the module made with the Teensy. How many euros do you have to spend for that?
So I think the Teensy itself is like $20, maybe.
Yeah.
Around 20. The audio shield, I think also like $20. Yeah, then pin headers, that's like penny stuff, you call it, I think. This we saw the connector to Eurorack, we soldered ourselves.
Yeah, so these are not available at Mutable Instruments, but they're open source. You can either order them yourself, the PCBs, and then you need to solder in pin headers and the jacks. but you can also buy them pre-made. I think Pusherman Productions has them, and they're, I think, 6 boards are €9 or something.
Yeah. So yeah, in total, I think like 55 euro.
Yeah, something around that. There's also, of course, other alternatives to the Teensy. For example, this is the Daisy board, and that's geared a little more towards, or that's geared completely towards audio development.
Yeah.
And we'll have Andrew Eikenberry talk about that, I think, in the last talk today.
Yes.
And it's a really, really great platform as well. So that would combine basically an audio shield and a microprocessor. And so, what was that? It was like $25 or something. So that's really great.
Yeah, but it has the audio codecs on it, so no need for a external
you don't need
codec.
an external board for the audio.
Yeah.
So, do we have any question from the audience? No.
I see a lot of chat about cool stuff we need to check out. Thank you, everybody, for that. So that's really cool. We're going to have to look through that as well.
So last question, because unfortunately, sometime at least from my point of listening, the audio was not always perfect, and so probably it's not going to be perfect on the YouTube stream. But I guess you did a registration of your own of the presentation that will be available somewhere.
Yes, we did that too. We tried to stream the whole thing in parallel on YouTube, so it's going to be on our YouTube channel.
Okay.
If everything, if all fails, we will probably just re-record it.
Yes.
I mean that would be another option.
Yeah, I'm sorry. The technical condition obviously is what it is, and especially for the audio, when you are just making a presentation with PowerPoint and voice, it's okay. But here we are in a more demanding situation, and it's far from perfect, unfortunately. But this was so packed of very useful information, so I think that that was really very interesting. So thank you.
Thank you for having us.
Yeah.
And so now we are going to move to the next talk, which is Romain Michon. So Romain is a full-time researcher at Gram. Previously, it was at Karma at Stanford. It's still at Stanford, but not presently with the lockdown. He is involved in the development of Faust since 2008, and it's now part of the core Faust development team here at Gram. And beside that, Romain's research interest involved embedded system for real-time audio processing, human-computer interaction, new interfaces for musical expression, and physical modeling of musical instruments. And in this talk, he is going to present how to build and play and program the gramophone. So, Romain, it's your turn. And maybe we will have a surprise after your talk, right?
Absolutely. It's great to do all here. Yes, because this is asking me for lunch. Because I'm deep down in the company right now. I'm show you after this presentation to local dish, which is called so about that. Presentation is recorded. So
I don't know, Romain, sorry, Romain, the sound is completely haché. So what can we do for that?
Maybe because training, people say it's for them.
Sound is bad, yes, yes. Sound is fine, good for me as well. Okay, so it depends.
I train from two so one of the videos starts, it will be okay. Well,
okay, go on, Romain. For some people it's okay, and not for me, but it's not a problem.
Hi everyone, my name is Romain Michon and I'm a researcher at Gram. During this 1-hour workshop, I will teach you how to build your own gramophone. That is the gramophone. And I will show you how to use it to make your own musical instruments. Now, before we get our hands dirty and actually start building our own gramophone, we need to answer a simple question. What is the gramophone? The gramophone is a mobile standalone musical instrument programmable with Faust. Sound is produced by a speaker and it is completely battery powered. The battery can last about 24 hours while it's on. It hosts various sensors that can be used to control the generated sound. You will find motion sensors, such as an accelerometer and a gyroscope, multiple rotary potentiometers, and light sensors, which is a photoresistor, basically a microphone, and a button. Yes, a button. They can all be mapped to sound synthesis parameters, as you just saw, directly from the Faust code. And that's something that we'll see later in this presentation, how that works. Other elements of the gramophone allow you to turn it on and off, to cycle between different Faust programs, to plug headphones, or to wire it to a mixer. The gramophone can be charged using a micro USB cable, which you can see here. The same cable can be used to connect the gramophone to a computer to program it. Now, some of you might be wondering, why the heck would you want to make this thing? So the first question we will answer here is why the gramophone? The gramophone has been created as part of the Amstramgram project. Amstramgram is a STEAM project bringing together services and resources for the educational community. The main goal of Amstramgram is to make abstract scientific concepts more tangible and concrete through musical creation and computer programming. Scientific concepts are explored through the programming of the gramophone thanks to the Faust programming language. Students eventually work towards a musical project with their teacher. And over 160 gramophones have been built and are already touring in the middle schools of the Auvergne-Rhône-Alpes region in France. So that is why we're making the gramophones. Besides that, they're fun to play and they can be used to write electronic music pieces. Okay, so let's now get our hands dirty and learn how to make a gramophone from scratch. These instructions can also be found on the Amstramgram website at the URL below. We will assume in this tutorial that you know how to solder and that you have some experience with hardware in general. Let's first have a look at the components which are needed to build the gramophone. By the way, feel free to get back to this list whenever is appropriate. You can also find it on the Amstramgram website at the URL below. First, you will need to acquire the gramophone case. While it cannot be purchased directly, the STL files of the case can be downloaded on the Amstramgram website and then printed using a 3D printer. If you don't own a 3D printer, which is the case of most people, you can also have them printed online and shipped to you. There are many websites that provide this service. I won't mention all of them here since they vary from one country to another. You will need a LilyGo TTGo T audio board, which is the heart and the brain of the gramophone. It is based on an ESP32 microcontroller and it hosts motion sensors and an audio codec. You will need an IAMA 3-watt speaker. Make sure you get exactly this speaker model, otherwise it won't fit on the gramophone. Or, by the way, you could just download the source files of the case of the gramophone and adapt it to anything you want. The gramophone is a completely open source project, so all the sources are available online on the Amstramgram website. You will need a 3.7 volts 2050 milliamps per hour battery. Make sure you get exactly this model, otherwise it won't fit in the gramophone. That's just like for the speaker. By the way, we're sorry if we're showing you the links to retailers in Europe, but at least you will be able to get the part reference this way. You will need a small battery connector. There should be one that comes with the LilyGo TTGo T audio. You will need a 3-position switch. This kind of switch should have 6 pins at its bottom. You will need a set of 2 10K rotary linear potentiometers with their corresponding knob. Of course, the color of the knob doesn't really matter here. You will need one large 22 by 7 millimeter washer. You will need one 18 by 6 millimeters washer. You will need 6 7 by 4 millimeters washers. You will need a rotary encoder with an integrated button, 6 10K resistors, 1 photoresistor, 4 YLF TF 2.5 by 10 PZ1 AB SPAC screws, 10 YLF TF 2 by 10 PZ1 AB SPAC screws, 1 250 by 25 by 1.4 millimeter strap, 1 25 millimeter strap buckle. Let's now have a look at the supplies you will need to build the gramophone. Feel free to get back to this list whenever is appropriate. You can also find it on the Amstramgram website at the URL below. You will need electrical tape, white, red, and black 22 AWG stranded wires, heat shrink sets, solder. You will need 10 wires ribbon cable. Here I'm holding 2 of them next to each other's. 1 female IDC-20 plug. Okay, now let's have a look at the tools needed to build the gramophone. You will need a small plier. You will need a small wire cutter, a medium-sized plier, 1 8 and 1 10 millimeter wrench, 1 small Phillips screwdriver, 1 pair of tweezers, 1 stripper, 1 dentist tool, 1 heat gun, 1 multimeter, 1 soldering iron. This time, we're ready to build the gramophone, so let's get our hands dirty. The first thing we need to do is to prepare the components before we install them in the gramophone. The first one we will take care of is the ribbon cable and the female IDC-20 plug. Cut 2 sections of about 12 centimeters of the ribbon cable. You can use regular scissors for that. Then put the 2 cables next to each other and slide them into the IDC plug. Once they are perfectly aligned, you need to force press the plug. There are special tools for that, and I don't have access to them right now, so I just used a clamp to do this. What's important is that the amount of pressure you apply on the plug is well spread on its surface, so using regular pliers is not a good option here. After you're done with this, you must separate all the individual wires and cut the ones that we won't be using as shown on the picture here. Feel free to pause the video at this point to look at this picture in more details. The next component we need to prepare are the 2 rotary potentiometers. They usually come with a small strip that needs to be broken using a plier. Just grab it with a plier and pull it. You'll have to do that on both potentiometers. Next, you shall solder the 10K resistor on the left and center pins of the potentiometer as shown on the picture here. We recommend you to pre-solder the pins to facilitate this operation. Make sure you bend the pins 90 degrees before you do that. In fact, you can see on the picture here that pins are bent. That's a very important step. You should cut the legs of the resistors to keep things clean. Put a heat shrink on the resistor. You should of course cut it to the right size, then shrink it using the heat gun. Let's now prepare the encoder. The encoder should have pins on 2 sides, one with 2 pins and one with 3. Solder 2 10K resistors to the side with 3 pins as shown on the picture. There should be 1 resistor on the left and right pins. The center pin should not be used for now. As for the potentiometers, pre-soldering the pins should make this operation easier. Now solder the 2 resistors together as shown on the picture. You should cut the legs of the resistor to keep things as clean as possible. On the back side of the encoder, solder a wire between the center pin near the resistor and the left pin on the other side. Now that the encoder is ready, solder a 10K resistor to one of the pins of the photoresistor. This type of component doesn't have polarity, so you can pick up any pin you want to do this. You can protect and insulate the pins of the photoresistor using heat shrinks as shown on the picture. This will prevent potential shorts in the gramophone. Solder a 10K resistor to the button. As the photoresistor, the button doesn't have a polarity, so any of the pins can be used for that. We can now prepare the speaker. First, cut 2 wires, one black and one white of about 14 centimeters each, and strip them on both ends. Make sure that you remove a very small section of the insulant on one side because the solder points will have to be very small on that end. We also recommend you to pre-solder the wires at this point. Now solder the black wire to the negative pin of the speaker and the white wire to the positive pin. Make sure that you use the side with the long strip on the speaker. The small solder points on the other side will be carried out later. Let's now prepare the battery. Be careful when manipulating the wires of the battery to not create a short. Lithium batteries can be slightly dangerous in that regard, so let's be careful here. Cut an 8 centimeters long red wire and soldering to the red wire on the battery to extend it. Then make sure to cover the solder joint with a heat shrink. Then solder the battery plug only to the black wire of the battery as shown on the picture. Insulate the solder joint as well as in the previous step. Finally, insulate the yellow wire that we won't be using for this project at all. Okay, we're now ready to prepare the 3-ways switch. Pre-solder the 2 leftmost pins of the top row and the 2 rightmost pins of the bottom row as shown on the picture. Now that all the components are ready, we can start assembling the gramophone. First, mount the first potentiometer as shown on the picture. It should be placed between the square hole and the large circular hole. The pins should be oriented towards the larger end of the case. Make sure it is fastened properly using the 10mm wrench. You can then mount the second potentiometer on the case. Look at the picture to figure out its location. The pins should also be oriented towards the larger end of the case. Make sure it is fastened properly using the 10mm wrench. Let's now mount the encoder. Note that the side with the resistors should be oriented towards the larger end of the gramophone. Make sure it is fastened properly using the 10mm wrench. Again, we can now mount the button on the gramophone case. The orientation of the pins doesn't really matter. In order to mount the switch on the gramophone, we first need to place the 6mm washer on it. You can then place it in the gramophone as shown on the picture. Once you put it through the corresponding hole, put the 7mm washer on the other side and then fasten it to the case with the bolt and the 8mm wrench. Put the photoresistor in the hole highlighted on the case with some kind of ring. You really can't miss it. It should just press fit in it, so you might have to push a bit on the photoresistor to go in its housing. Optionally, you can put some hot glue at the back of the photoresistor inside the gramophone to hold it in place. Now that most of the components are mounted on the case, we can start wiring them. Cut a small section of black stranded wire, strip it and pre-solder it, and then solder it as shown on the picture to the bottom right pin of the switch and to the left pin of the potentiometer right next to it. Do the same by connecting the left pin of the same potentiometer as in the previous step to the center pin of the encoder on the side with the resistors. Continue this chain by connecting the same pin on the encoder as in the previous step to the 10K resistor soldered to the photoresistor. Connect this last point to the left pin of the neighboring potentiometer as shown on the picture. We can now end this chain by connecting the last pin of the previous step to the 10K resistor soldered to the button. As you probably understood it, this wire is for the ground, so let's now bring power to the components using the stranded red wire. Connect the rightmost pin of the potentiometer right next to the encoder to the resistors of the encoder itself. Continue the chain by connecting the resistors of the encoder to the left pin of the photoresistor, which is basically not the one with the 10K resistor soldered to it. It's the other one. Continue the chain by connecting the photoresistor to the rightmost pin of the neighboring potentiometer. Finally, end this chain by connecting the potentiometer from the last step to the pin of the button without a resistor soldered to it. We're now ready to solder the ribbon cable to the gramophone. It will be used to connect the various components of the gramophone to the LilyGo TTGo T-Audio board. Solder the leftmost orange wire to the right pin of the potentiometer next to the encoder. This is basically the ground. Then solder the yellow wire to the left pin of the same potentiometer. This is power. After that, solder the green wire to the center pin of the potentiometer. The next wire on the ribbon cable is the violet one. You should solder it to the right pin of the photoresistor, which is basically the one with the 10K resistor soldered on it. You want to solder the violet wire to the pin itself, not the resistor, of course. The next wire on the ribbon cable is gray. Solder it to the center bottom pin on the switch, right next to the black wire. Then comes the red wire, which should be connected to the center pin of the potentiometer next to the button. The following orange wire should be soldered to the right pin of the encoder on the 10K resistor side. Here is a close view of the encoder so that you don't make a mistake. The following gray wire should connect to the encoder as well, but on the other side than the previous wire. It should be soldered to the pin without another wire soldered to it. The next wire is white, and it should be soldered to the leftmost pin of the encoder on the side with the 10K resistor. Finally, the black wire should be soldered to the pin of the button with the resistor on it as shown on the picture. We now need to connect the battery to the system. Solder the two red wires coming from the battery to the two remaining pre-soldered pins of the switch. The speaker can now be mounted on the front face of the case using the 4 YLF TF 2.5 by 10 PZ1 AB SPAC screws with the small washers. There is no specific orientation for the speaker. Just put it the way you want. We also recommend you to cover the speaker driver with electrical tape to prevent potential shorts in the system. That's an important step. Actually, don't miss it. Make sure that the black and white wires of the speaker come out on the other side of the gramophone, along with the ribbon cable connector and the battery. On the Liligo TTGO T-Audio, cut the two leftmost and the two rightmost pins of the male IDC connector as shown on the picture. You can use a small wire cutter for that. Now spot the future position of the board inside the case. The two remaining circular holes on the case should be for the microphone on the board and the jack audio output. Connect the battery to the board as shown on the picture. The battery will go behind the board, so you should take that into account. Connect the female IDC connector of the ribbon cable to the board as shown on the picture. The orientation of the connector matters, of course. Put the board inside the case and fasten it using two of the YLF TF 2x10 PZ1 AB SPAC screws. Make sure you put small washers between the screws and the board as shown on the picture. The battery wires should come out as well as the speaker wires. Solder the two speaker wires to the board as shown on the picture. The black wire should be connected to the negative pin and the white wire to the positive pin. Put the battery in the case on top of the board and put a thin layer of foam on it so that it is holding in place when we close the case. We can now prepare the strap. Attach the buckle to it by sewing the strap on itself. You could also staple it if you don't know how to sew. Burn the ends of the strap to prevent it from shredding. Install the strap in the back of the case as shown on the picture here. Buckle the strap up and the back of the case should be ready to be mounted on the gramophone. Close the box with the small screws. Mount the speaker grid on the gramophone and fasten it using the remaining small screws. You should respect the orientation on the picture. Finally, yes, finally, put the knobs on the potentiometers and the encoder. Your gramophone is now ready for showtime. Now that you have a gramophone, you probably want to learn how to use it. Since we don't have a lot of time left in this presentation, we just want to give you an overview of how the gramophone works in practice. Okay, so the first thing we want to do in order to be able to use the gramophone is to write a Faust program. And the program we're going to write here is going to be very, very simple. It's just to demonstrate the various features of the gramophone. So, so let's do it. So the first thing I'm going to do is I'm going to use the sawtooth wave oscillator because we love it. And as any sawtooth wave oscillator, because it's an oscillator, it needs a frequency. And I'm going to declare the frequency of the oscillator in a variable here, and I'm going to call it freq. And freq is going to be controlled by a slider in the generated user interface here in the Faust Web ID. By the way, guys, we're using the Faust Web ID here, which you can find at faustide.gram.fr. It's free, it's great, and you can use it to program the gramophone. Okay, so we were going to use the slider to control the frequency. And the first parameter of the slider is the name of the slider, and I'm going to call it freq, just like the variable to which it is assigned. The default value is going to be 500. The minimum is going to be 50. The maximum is going to be 1000. And we're going to use a precise step of 0.01. Okay. So now we have a sawtooth wave oscillator, and its frequency is controlled by a horizontal slider in the generated interface in the Faust Web ID, which we're not going to use right now because what we want to do is to control the gramophone. Okay. So the next thing I want to do is to be able to turn it on and off. And to do this, I'm going to create a gate variable to which I'm going to assign a button. And the name of this button in the interface is going to be gate. Okay. And all I'm going to do here is to multiply the sawtooth oscillator to gate. Sweet. So now I can turn it on and off, and I can control its frequency, but the sound that it's going to produce is probably going to be a little bit boring. So I'm going to use a cry baby effect, which is literally a wah pedal. Okay. And it has one parameter, and that parameter is wah. You can actually see that if you look at the documentation of the function just by hovering it. And you can see that the wah parameter is the pedal angle from 0 to 1. So here I'm going to create a new variable, which is going to be controlled by a slider. And the name in the interface of the slider is going to be wah. And I'm going to say that the default value for it is 0.5. That's like the middle of the range. The minimum is going to be 0. The maximum is going to be 1. And we're going to have a precise step of 0.01 as for frequency. Great. Okay. So now I can control the timbre of the sound. I can control the pitch of the sound, and I can control the fact that it's on or off. So that's enough for what we want to achieve here. So now if I want to use this program on the gramophone, I still have to connect those user interface elements to the various sensors which are on the gramophone. The motion sensors, the accelerometer, the gyroscope, or the physical controllers which are on the case of the instrument, like the potentiometer or the button here. Okay, so let's start with the button. The way we do this is by using metadata. And here, all I'm going to say is that switch 1, which corresponds to this guy on the gramophone, is going to be assigned to the gate parameter. So it's not a switch, it's a button. But, you know, we're French, so we do make English mistakes once in a while, you know. And so, so even though we say switch, we do mean button here. This is not a switch. Well, it depends on how you use it, but it is a button. Okay. Then I want to be able to control the frequency parameter with the potentiometer of the gramophone. So this one, because this potentiometer here is always for the gain. It's always mapped to control the gain, so the volume of the gramophone while you play it. So you can access this one with the metadata. But in practice, you never really do this. So we want to use this potentiometer here. And the way we do this is by saying knob colon, and this is knob number 2 because knob number 1 for gain is here. Okay. And finally, I want to control the Y parameter using the accelerometer. And the accelerometer metadata in Faust is standard. That's not just for the gramophone, that's for everything that has an accelerometer, and it's ACC con. And then you need to configure it. The first value I'm going to put here is going to be 0. That's the axis of the accelerometer. And 0 is for X, 1 is for Y, and 2 is for Z. Then you can map a curve, and I'm going to use curve number 0. I'm not going to explain to you what it does here, but if you're interested, you can just look at the Faust documentation to know more about it. And then those are acceleration parameters, and I'm not going to explain them as well. You know, like if you really want to know what this does, just look at the Faust documentation. I think that's the best way to do this. Okay. So Y is going to be controlled by the X-axis of the accelerometer. The knob is going to control the frequency, and the button is going to control the fact that the gramophone is on or off. Sweet. So this is ready. All I have to do now is to go in the export function of the Faust Web IDE, click on platform, and then choose ESP32. And architecture, I'm going to use the gramophone flash. Then you just click on compile. And after some time, you should have a gramophone program that should just be produced and that you can download on your gramophone. And I'm going to show you how to do this in this next step. Okay, so after about 15 seconds, you should have a QR code that displays to your screen, and you are now able to download the gramophone program that was just generated by the export function of the Faust online compiler. So you just download it. After you downloaded it on your computer, you can use the Grammo loader, which is this little program here. It's free. You can find it on the Amsterdam website, and it's free to download. It works on the Mac, it works on Windows, it works on Linux. You have different versions, and all it does is that it creates some kind of bridge between the Faust Web IDE and the gramophone. Okay. So in order to do this, you just have to select. Okay, of course it's in French, you know, like, but you just have to get used to that kind of stuff, you know. Like eventually we're gonna make an English version, but there are so few things to know about this program because it's so simple that for now, French is gonna be the rule. Okay, so here I'm just gonna choose the file that was downloaded on my computer. It's binary.zip, and binary.zip landed on my computer in my downloads folder. And I'm just gonna select it and I'm gonna open it, and then the programming of the gramophone will start happening. This operation will take about 20 seconds. So I'm probably going to see you after that. And eventually, once it's done, you will get a message in the Grammo loader application that will tell you that the programming of the gramophone was a successful operation. So let's wait for it. Okay, it just happened. So now we're actually ready to play with the gramophone. You just put it on your hand. By the way, I don't know if you saw that, but the strap is slightly lower on one side than the other. It points towards the ground, you know, so that's where you should put your hand. Don't hold it like this. You have to hold it like this, okay? And eventually, if things actually worked the way that was planned, if I press the button here, I should hear a sound. And it makes a sound, so we're actually happy. So audio is being triggered by the button. I can control the frequency with the knob here. Nice. And I can control the gain with the gain button that I just have over here. And I can control the wah parameter using the accelerometer. Nice. So that's pretty much everything you need to know about the gramophone. One feature that we didn't see yet, is the fact that you can switch between different FAUST programs installed on the gramophone using the encoder here. I'm not going to show this feature for now because we don't really have time for it. Finally, one thing you need to know is about this little switch that you have here. This switch allows you to turn the gramophone on in battery mode. So if the switch is at the center position, it's a neutral position, the battery is not connected to the gramophone. So in that case, if you unplug the cable, you will lose sound. Because now the battery is not connected anymore to the gramophone. On the other hand, if you want to connect the battery to the gramophone, you have to go from central position. Once again, there are 3 positions, left, center, and right. At least from my perspective, it's probably different from yours. So here, if you push it towards the knob next to it, it goes in battery mode. And now you should be able to play the gramophone with the battery. Okay, and finally, the other position with the switch allows you to force the fact that the gramophone is being programmed, because sometimes it can be stuck. All these informations are better documented on the Amstramgram website, so I just recommend you to have a look at it. Okay, so one last thing to conclude this little tutorial. Once the connection is established between the FAUST IDE and the grammar loader through binary.zip, you don't have to select it again afterwards. So it means that all you have to do if you make some changes to the FAUST program here is to click on the export button. And just clicking on the export button will produce the gramophone program and will also install it on the gramophone connected to your computer. So you don't have to select the program once again. That's it, folks. If you have any questions, feel free to send them to me by email. I hope you enjoyed this presentation. Okay. There we go. Sorry, it's kind of a complex setup here. So yeah. Yeah. So I will take questions if you have any. I think I replied to most of the questions that were asked in the chat. But yeah, if you have some live questions, feel free to ask them.
Maybe I have 2 questions, Romain. What about the price of building a gramophone?
It's a good question. So if you just get the parts and if you have the case 3D printed somewhere else, so if you don't have a 3D printer, like the total price is about 110, 120 euros or something like that. But if you have a 3D printer and you print the case at home, of course it will be even cheaper than that. So it will be more like 80, 90, maybe like, yeah, actually 70 or 80 euros or something like this. So yeah.
Can you also explain the difference between the FAUST IDE in normal mode and the FAUST IDE in Amstramgram mode or gramophone mode?
Yeah, it's a good question. So basically, in Amstramgram mode, the IDE is much simpler than in the regular mode. So many of the features are hidden, so that students who are like, once again, middle school students don't change parameters, which might completely screw up the setup of the FAUST IDE and don't have any sound coming out of their computer. So yeah, the whole idea is to prevent students from doing something stupid, basically. So yeah, it's the same, but with less features.
Are there any questions from the audience?
Yeah, I'm sorry if this was a little bit dry, but you know, like I mean, this was supposed to be a workshop where people actually make something, you know, like and of course, this is not something that you guys could have done in that case, you know, or we could have better prepared things, you know, and ask people to pre-order parts to build their own gramophone at home, you know, like but yeah, so at least we hope that this will be useful to people who actually want to make the gramophone later, you know. But yeah, I'm sorry if you know, like all these technical details are not so so interesting potentially, you know, in that context, you know, like but that's what online workshops on hardware are, I guess. So yeah.
Okay. Are there any questions?
Is the gramophone more compatible with other ESP32 audio boards? Well, not really, because there's the well, if you want to make a gramophone which has exactly the shape of the one that you that we have here, with the STL files that are provided on the Amstrongram websites, the form factor of the board is very very important. And so only that specific board will properly fit in the gramophone. So of course, you know, like I mean, you could get another board, and because you know it's an ESP32, you can program ESP32 with Faust pretty easily. You know, like that part doesn't really change. But you could adapt the STL files of the gramophone case so that they fit with another board. But if you want to use another board, you'll have to change the files of the case of the gramophone probably. So yeah, I saw there were other questions in the chat, but I don't see them here. Maybe Jan, you can moderate the questions in the chat. Okay, no, I can see them now. So
okay.
How are the TTGo built-in codecs WRT SNR? Is it advised to use other codecs for performance applications? Well, that is a good question. So the codec in the on the TTGo T audio board is the same as the one on the iPhone. So it's actually relatively good quality codec, and so the sound quality of that codec is actually pretty good, you know, and there are a few weird things on the TTGo T audio board, especially the wiring of power on the codec in relation to Wi-Fi on the ESP32 board is not really done properly. And so there are some features of the board that you can't really activate if you still want to have audio running on the system. But if you just use it for basic applications, the audio codec is actually relatively good quality on the TTGo T audio board. So yeah. Okay, there are many questions. So okay, then could the gramophone be modified to accept audio inputs so it could work as a sound processing unit? That is also a good question. So there is a microphone on the gramophone, so that is an audio input, but I guess that doesn't really answer your question. So the TTGo T audio board, weirdly enough, doesn't have any physical line inputs on it. However, the audio codec on the TTGo T audio board has a stereo line input on it. It's just that it's not wired at all. So if you're very good at soldering, And if you have very good eyes, and if you don't shake too much, you could potentially solder wires directly onto the codec of the TTGO audio board to retrieve the audio inputs. I think that's the only way to do this. And it's probably hard to do. Well, I mean, it's not so hard like from a technical standpoint, but like soldering on an audio codec by hand is pretty intense. But I've done it before, and it works, but it's hard. Okay, so there are more questions. Okay. Okay. There are comments, but I think that's all the questions that were in the chat, right? Or maybe I missed some. Or okay, cool.
Okay, so thank you very much, Romain. It was very detailed and very. I think that you can really rebuild the gramophone from this video. So it's going to be super useful, especially because we don't have we built some of them for our purposes, and we have more than 100 of them, but yeah, we don't have a unit to fabricate them. So
yeah, Thomas Hopman made very good comments about this actually in the chat. You know, and the fact that we don't make PCBs for the gramophone yet. We actually made a very like primary version of the gramophone with a PCB, and it's true that in terms of putting it together, it really helps. But I think in our case, and the way it is used and provided to people in the framework of the Amsterdam project, it was kind of easier to do it the way we did it. But it's true that using PCB would definitely make things easier in terms of assembling the whole thing. So yeah, maybe a future version, but I feel like for now, and also from a pedagogical standpoint, which is also like something that I didn't really talk too much about in the video, but there are actually students who are going to make their own gramophone in some middle schools, you know, and the soldering aspect of things, you know, and wiring things and cutting wires was something that was actually really asked by the teachers. So that's also one of the reasons why we did it like this. But yeah.
I don't know if you saw it, but there is a question by Peter Kim about the availability of all this information.
So whether this video was the first documentation or I may have missed a GitHub repo for the gramophone. Well, everything is on the Amsterdam Git repository, which I posted earlier in the chat. So if you scroll up in the chat, okay, and they are, but they are deleted in the end. So, okay, let me. The problem is that I have a complicated. Yeah, there we go. Amsterdam making. Okay, so that's yeah. You found the source. You found the source of what's on the Amsterdam website, and it's a markdown file. So in terms of making the gramophone, everything is here for now. You know, because we'll just assume that the video are the instructions. So yeah.
Okay, so thank you again, Romain. This afternoon we will have also 3 talks. Don't miss the first one, don't miss the second one, and don't miss the third one. The first one will be by Xiong Ren, and Xiong is the guy that did the Faust IDE during its internship here at Gram. So it's a very bright programmer, and he's doing a completely new project, which is Faust, how to say that, a graphical editor for Faust. And so it's probably a solution to learn Faust much more easily than with the textual language itself. It's a kind of Max, but directly in Faust. And then we will have a talk by Stefan Letz and presenting how you can use Faust to make VCV rack modules directly from Faust and using also the Faust IDE. And finally, we will have a talk by Andrew Ekenberry, which is the author of or the designer of the DAISY board, which is a super interesting board, especially because it has all the audio already wired on the board. So don't miss this afternoon, and so we will have a lunch break. And I don't know, Romain, if the invitation of coming to your house for having a truffade is still
Okay, so the thing is, we, you know, like usually in France, before you eat the aligot, you need to drink the aperitif. And the issue is that aligot is something that you have to eat on the spot, because it has to have like the perfect texture for it. But however, I'm just gonna give you the recipe before I actually make it. You know, like so. But we need to take the aperitif first. So that's why. But basically, you need nice mashed potatoes in which you will add a lot of cream. Because in the mountains in France, we like cream a lot. So we put cream in everything. Okay, and because that's not really just fat enough like this, once it's hot and warm, then you can add this thing, which is a very specific kind of cheese that you find in the mountain in France. It's called Tome Fraiche, and it's very soft. And so you add the cheese to the mashed potatoes, and then eventually with some garlic, you mix it all together. And eventually, when you mix it, it will become this sort of paste, and it's going to be very tough to do. Like you need to have like very strong arms, otherwise it doesn't work. Like sometimes you even break the spoon because it gets so hard. You know, and eventually you eat that with the prosciuttos and salami. So we'll probably eat that in about an hour here once the aperitif is done. But yeah, if you want to know the recipe, I can send it to you. I can send it to you directly in the chat or by email. You know, it's very easy to make. The hard thing is to find the soft cheese, which you can only find here, basically. So yeah. Anyway, bon appetit, guys, and see you later this afternoon.
Okay, bye-bye, guys. See you this afternoon. Don't miss the aligot and the 2 p.m. talk. Bye. Ouais. Okay, so Aline, are you? Well, we have 3 minutes left, and then we will start.
C'est pas Aline, c'est Chion.
Ah,
C'est Aline.
ah merde.
C'est comme ça.
Okay, so maybe I will start with a short introduction to Xiong and his talk. So Xiong Ren is a composer and researcher in computer music. He entered the Conservatoire National Supérieur de Musique et de Danse of Lyon in 2011 and he graduated in 2016. He also did artist diploma and followed the cursus de composition at IRCAM. He is also a PhD student at l'Université Jean Monnet, and it's a very close collaborator with us. He did as I mentioned this morning, it is the author of the Faust IDE, and he's going to present us its last tool, and which it's the first public appearance, right, of Xiong of this tool.
Yeah.
Okay.
It's the
So
first.
okay. So Xiong, I think it's.
Yeah. Okay.
Thank you.
Hi everyone. Yeah, I hope everyone had a good meal. And yeah, this is stream from China, so I'm hoping it's going smoothly. I'm going to share my screen, my tab. Can you see my tab or this slide? Okay. Yeah. So welcome to my presentation workshop. So this is a design pattern for Faust DSP with a web-based graph editor. I would like to show you a tool that I made recently, which can be used for to design false DSPs in maybe a more straightforward way, just in a web browser. So yeah, first of all, I want to talk about why I chose false as the language to use in our DSP design workflow. Well, the reason is that if your DSP is already written in false, it actually means that the DSP can be quickly exported with false ID or some online service or with your false compiler to a large variety of platforms. And the other reason is that, which is also a most important one, that everything in false can be considered as an audio stream. The false, the name is combined from functional audio stream. So everything is audio stream and everything is functional. So the way we design false DSP is just like connecting audio cables between different inputs and outputs from analog audio devices. So this reason actually brings us to the main purpose of this language. In fact, false language is designed to be an interpreter to calculate from an audio graph to some machine-readable codes, low-level codes. So it provides a very efficient solution to let us be able to describe some complex audio graphs into plain text. Then it's up to the compiler to make these texts understandable by machines. This process is called block diagram algebra. So yeah, this block diagram algebra is the powerful side of this language that takes care of both human users and machines. Its text-based form might be a sweet point, but it is still not easy to learn. Yeah, maybe Jan, you'll not agree with that, but from my experience, it's not so easy because to write in false, you need to learn how to manually translate a graph into the code. It means to flatten these cables and connections into plain text. And this needs sometimes hard work, especially for beginners, for some sound engineer, sound designer, or artists. So, for example, without compilation, there's also some difficulty that we don't always know how much inputs and outputs these modules actually have if you are importing these functions from the library. So yeah, fortunately, a bunch of tools are provided to make the coding experience much better. That is why I wrote last year with Graham's colleagues the new False IDE, in which users can watch your block diagram of the code written in real time, and you can test it with multiple visualizations. You can debug it very quickly, and just in the browser. So this is a big step, or even like a game changer for us to make the language more accessible and user-friendly to false developers. Yeah, so after having this false IDE, I'm thinking about if we can go deeper or go further to this user-friendly way. So yeah, I can share this. Yeah, maybe later. I will post it in the chat. This slide. So yeah, here's as false code is already a representation of an audio graph. Why not just generate it from a graph automatically? And that's so that we can design a false DSP without any coding. Here's what I imagined. We can, from left to right, we can start from a graph in the browser. We can do some patcher, and it generates automatically the corresponding code for you. And then you can test it or having this block diagram to recheck if it corresponded to your graph and just in time and just in the browser. So this approach is also used by Gen. If you're familiar with Max, you might know that Gen is also a graph-to-code generator. There's a language called Gen Expert, which is also an intermediate step between. Yeah, maybe. It's the code is intermediate step between the graph and the DSP code. So you can also export this code into C++ code after you're having this graph or this Gen Expert code. So actually, I used Gen when I was making project in Max. So I think it would be nice if our Faust graph-to-code generator can handle shares the same behavior as Gen to facilitate Gen users or Max users to switch to Faust and export maybe to more destinations or platforms. Here are 4 behaviors in Gen that I implemented in the Faust graph-to-code generator. First is these boxes that represent a function that takes some arguments or inlets. Note that if you predefine one of the arguments, it will actually replace one of these inlets and replace them into a constant value. Then graph connected with these boxes is called a patcher. Secondly, when Gen analyzes this graph, it will iterate all the outputs and search the connections above. So without any connection, its inlets will be the default value, so 0. Then multiple connections into the same inlet will automatically be merged and added together. So this is the second image shows, and beside its code. So the out3 is without any connections from its inlet, so it will be 0. And out1 is the merge of in1 and in2. And if you need to introduce a loop into the graph, it should be delayed by at least one sample by the history operator. So this is similar to Gen's tilde, which is recursive composition operator. And Gen also supports 2 types of subprocess. You can use a code box to write Gen's code, or put a subpatcher. These subprocesses are especially useful when you want to reuse it in different situations. And then with these basics, how do we generate the false code from a graph? Let's take a look to some examples from these functions. We know that all of them can be formed as one identifier as a result equals the function's name with parentheses and arguments separated by commas. So here, from right, we have ma.sr, which is the sample rate. It has no input, so no arguments. Then the sign has one input and one output. So here it's sign 0 because it doesn't have any cables connections. For plus, it has 2 inputs and 1 output, and the os.oscrq, which is oscillator based on 2D vector rotation, is special because it has 1 input and 2 outputs. So we need to give an identifier for each of these outputs. So the code is a little bit longer. Here are some more examples to show how arguments and connections affects the code. With the graphs inputs, they have their index and identifier, and can be composed easily as a function argument. In addition to Jan's argument usage, you can use an underscore as a placeholder that allows you to omit an argument declaration and leave it as an input. For example, here we have, from the right bottom, you have the en.ar, which is attack release envelope. It needs 3 inputs: the attack time, the release time, and the trigger signal. Here we fixed the release time, which is the second input, to 0.1, and the first input goes to attack time because we put an underscore at first position, and the second input goes to the trigger signal. You can also put a function name instead of the underscore or numbers to use it as an argument. Also, we know that for some pattern matching related post functions, the number of I/O is variable. It's more like the compiler doesn't know by default how much input and output these functions have if you don't put arguments before. So like here you have si.bus 5, sorry. It should have 6 input and 5 outputs. So where the number 5 already occupied the first input, so it leaves 5 available inputs and outputs. You can declare by @in6 and @aus5, like in Max. You can have these properties to force these inputs and outputs. And generating a graph with a loop is one of the trickiest things in this system. We know that in Faust we need this recursive composition operator tilde should be used in a loop so that we can identify easily every loop in the graph. And this is actually Yann Oglaré's consideration, and he proposed to put all these loops outside the rest of graph, and then to facilitate the cable management. So in this case, we have the main graph has 2 inputs and 2 outputs, where one pair of them are used to build the loop. Yeah, you can see in this block diagram that the loop is outside the main graph. And here's an example of code block subprocess, where you can have some Faust DSP code as a subprocess. You can put directly the Faust code into this code editor, and you can. I use here the environment keyword you can see in the code to ensure that the subprocess is in a closure. Then just export the process function. And after each change of the code, I evaluate the code in this box to actually get information about the number of inputs and outputs, so that the outer graph can connect properly with it. And I also implemented the subpatcher that will be transformed into a width expression, in which you can use identifiers that are defined at the patcher at the parent level of the patcher. So here you can see in the doc represents the contain the inner side of the patcher object, and it's a max with 2 inputs and 1 outputs, and this can be reused multiple times if you want to duplicate it elsewhere. Yeah, and here's something that is quite special in Faust language, the iterators. more precisely, you have 4 iterators in Force language, which is par, sec, sum, and prod. They accept actually a subprocess with a variable that changes for each iteration and starting from 0. So this means the box that represents the iterator should have corresponding number of outputs with an additional variable output that attached to the subprocess. So here we have a par3 means 3 parallel processes as the output. So we have first 3 outputs, and with an additional one at the right side, the 4th one that will attach to our subprocess. And in this outlet, the variable iterates starting from 0, and we are going to have oscillators with 3 different frequencies. And this result of the oscillator actually connects back to par3 object in order to close this subprocess, and then the par3 can know which subprocess to iterate. And in the code, you can see this subprocess is transformed to a lambda function. The last thing we need in this system is some UI components. Just as declarations in Force, we can put some sliders, groups, knobs, and so on with its properties, the name, the main max, the default value, and the corresponding UI can also be generated in this web page. Okay, so yeah, maybe here we can start our workshop with some actual example of JSPatcher. Yeah, this environment is called JSPatcher, and I will post in the Google Meet this link that everyone can try out. Yeah, and I propose you to open 2 tabs, one with this JSPatcher and another with Force IDE, so that we can easily test our generated code. And yeah, you are invited using Chrome browser, because this web app is really optimized for Chrome. Safari will not work, and Firefox cannot do some copy-paste stuff of patchers. Yeah, and note that I just finished this version with a file manager this week, and yeah, I think there will still be some bugs not fixed yet. So you can ask me in the Google Meet chat if you're having problems or bugs. Normally, you just do Command S to save, or Control S in Windows system to save your patcher and refresh the web page, and everything can be working. Yeah, and another thing is that we have some limits about WebAssembly's memory. So maybe you also experience with Force IDE is after too many times, if you compile these forced DSPs, it will reach the limit of WebAssembly's memory. So when you identify that Force doesn't compile in IDE or in JSPatcher, you just need to refresh the page. Okay. Yeah, I'm already sharing this environment into screen. So the first thing we're going to do is create from our file menu a new Force patcher. So after doing this, you will have a tab called untitled.dsppat. DSPpat is the suffix of our false patcher. And if you press Command S, or you can do also save from file menu, you can save this patcher to the file system. We will call it 01 DSP path. Yeah. But now you can see in your file manager panel, you have this this DSP path already here, and this file manager will not disappear even if you refresh your web page or you restart your computer. It will always be there. It's just when you make some modifications of this patcher, it will display a yellow point to say that you are not saved yet this modification. So just press Command S or Control S in Windows to save it. Okay, so for the first object we'll create is a comment box that you can type actually things in it. This is a comment. You can press C on your keyboard, just in Max, or you can also press N to create a normal box, then type comment in it, and it will transform the box into a comment. And yeah, on the left panel, the first icon means you are writing the file manager, and you can also press the second one, which is a list of all the objects available in false patcher. So you can also type things in it and drag and drop the comments into the patcher. So that if it doesn't work, maybe it means your patcher is locked. So you can click on this lock to lock or unlock the patcher. So if it's locked, you cannot actually modify the patcher. For some cases, like the code, you can only edit the code when the patcher is locked. So yeah, you have two states of the patcher locking Max. So we were creating our first patcher with some math operations. Yeah, let's just start from constant value. So if you press N and type C, you will have an object called constant, or just C, followed by a number. We'll put 0.42 as an example. So in this, this box will actually output always the constant number 0.42. And we will create another object called out. Out1 means the first output. Just connect them together. And you can see in the code from the right side, you can press, click on this code button to show the actual code of your patcher, and you will see it already have the out1 equals constant, this constant box, which is 0.42. And actually this code changes when you have any connections changes in your patcher. So yeah, I will just put some comments here. Constant value. I do this. And if we are doing some math, maybe we will add some value onto it. Just type N and plus space, then 0.42. And we'll create another output here, out2. Now output 2 is not connected, so it's 0. And when I connect it, it becomes the sum. the sum of these two values. You can also having plus objects without any arguments, just have two inputs so that you can connect 20.42 onto it. And actually you will have the same result as output. Yeah, then we will maybe do all the other operations, not plus, but minus. You can do Command D or Control D in Windows machine for duplicate these boxes. Double click the boxes to change the code in it. So this is the fourth output. This is the third, fifth, divide, multiply. Okay, now we are having all 5 outputs in this process. So let's just have it test in force ID. So I'm going to switch to force tab here. And copy paste the code we are having, and we will do an offline plot to just having these numbers on the screen. So put your plot mode to offline and plot first samples. Yeah, so now you're having strips with these values. I think they are correct. Okay. Yeah, I don't know if everyone got this result, but yeah, I think we will just continue. So this is our first patcher. Let's just save it, close it maybe, and create a second false patcher. So here we will do our classical example of the djembe example, when I think everyone, if you firstly you have opened the false ID for the first time, you will see this example, and it actually outputs a physical model of a string that repeats and repeats. So we will just put the code here. You can have a code block with the code object like this, and I will post this code, this example code here. So you know these objects of coming from false standard library, and here in false patcher you already have all of them. So if you see not seeing the objects.
Ren, we still see your Faust IDE.
Oh, sorry. I need to switch. Yeah.
Thank you.
Yeah, thank you for the reminder. Yeah. So here, I'll redo the process. Don't worry. I will put code in object. I will put a comment here. This is code block, and I'm pasting our example code. So let's redo this example with a patcher. So you know, everything in false standard library are also available in this patcher. So you can find all this ba.posen, which is the one post every 10,000 samples function. So let's just put da.pose and 1 10,000. It has one output and it will be connected to pm.gmb. With all these arguments separated by space, connected, and pm.reverb demo. Reverb. And this output of Djembe should be connected to all of these two inputs of the demo. And dispatcher will have two outputs. Connect them together. Now we open code and it will generate a code a little more complex from the original one, but basically it's the same. So we put this in port ID and we are having a diagram. And yeah, and to switch tab, yeah, we are having this diagram and we can run the code. And it's working. So yeah, we will be able to run this code also in this JS patcher environment, but let's just continue with some other patches and test them in JS patcher. So yeah, I will just save this patcher as the second one. And we can start from build a third one, another patcher. Yeah, so in this patcher, we will build a very simple algorithm or DSP, which is the mean value of one period of incoming samples. So we will build a subpatcher and test it with the main patcher. So we can put a subpatcher here. You can put P for short or patcher. Yeah, the same thing. And you can actually double click the patcher to show what's inside. And you can also do Control Enter to display the patcher at the red panel. You can also modify it here. So we'll do this like this. So what's the algorithm for that? Basically, you have an input calculate, and you have a second input which will say how long this period is, how much samples you want to calculate for this main value. And the first thing we will do is delay our incoming signal for this period. We use this add to delay a false signal to some samples, and then you can minus the actual value from a sample that is n samples ago, like this. And then we do an integration. Just add all these samples together between this period. So we need to add them together with a loop, that feedback. like this. And here we have the sum of n recent values. And the last thing is to divide it by the number of samples we measure. And output. You can see the algorithm here. And in order to test this, we may want a sample integrator with one value incremented each step by 1. So the same thing here. Plus, we can do copy paste actually. Okay. And we also need to decide the length of our measurement. So let's put 400. And out 1. Okay. So this should be, if it works as expected, after 400 values, you will have the sum, the mean value of the sum of the first 400 value. So let's put the coding for ID. I don't know if the add doesn't exist. Maybe you are not in a forced patcher, you are in another patcher. So make sure you choose the forced patcher in your file menu. Let's put here in forced ID and plot offline. And you will see here the 400 value. You will have a result of like 200 or something. So it works. Okay. The next thing, if we already have the algorithm of this mean value, we can actually build an RMS measurement in our force patch. So let's just save this one. Oh, I think we should do it quickly. So maybe just copy paste this patcher here. So in order to do a RMS, which is root mean square, in fact, you have 3 steps. The first step is do a square each values. And you already have the main these values. So we will put another 400 here.
Sorry, we are seeing again just the Faust.
Yeah, sorry. Sorry again.
Thank you very much.
Yeah. So I'll put some comment here. This is square. And you have the mean. And then the root. Okay. And we will be able to display these the value in bar graph in Faust's UI. So it's called IMS from 0 to 2. And you will need a attach for that you doesn't lose your signal and the signal doesn't be considered as 0 of 1. So this will show a root main square of the input value, and let's just test it in our patcher. So we just need to resave it 04. And let's create a JS patcher, which is a little bit different. It's not a Faust one, so it will not generate code, but it's a runtime for you to execute or compile the Faust code or compile this graph. So now you're having a new JS patcher in which you can put a Faust patcher inside using pfaust with a path. So the path is 04.bsppath. Yes. And I don't know, maybe an oscillator. But this is a web audio oscillator, which is not coming from Faust, but we can build an oscillator from Faust later. We don't have much time today, but yeah. So to have this UI, we can simply type UI or Faust.ui because it's under Faust namespace. So if you type Faust.ui, you will have this empty box in which you need to connect from the last output of pfaust and connect it back to the first input. There are keyboard shortcuts go in and out. Yes, it's actually command click the space in the patcher. Yeah, so you will also need a bang. You just press B on your keyboard, and you will have this button. You can lock the patcher to ban this Faust patcher in order to have this graph, this UI. And after connect this oscillator, make sure that you also click this. You have this little button. It's an audio switch. You need to enable it to have your audio. And I think it's not working. Let me see. So I don't know why it's not working. Maybe it's because Faust is not compiling. Okay, yeah, I don't know why you need to connect the output of Faust to some destination in order to get it to work. So here is an object.
Got optimized away, maybe.
Sorry?
Maybe the output just got optimized away. I mean, Faust is highly optimizing.
Yeah, I think it's more web audio optimization. If it's not connected, it's not working anymore. So here it will work if you connect this live gain object to the output of this pfaust. You can listen to it. If you put audio in. And yeah, this output, yeah, it's not this output. And it's this one. Okay, this output is not actually a signal to hear. So yeah, we'll have this RNS. And yeah, this to test it, maybe we can just do it like this to actually change the volume, and it works. Yeah. And let me see what else can we do. Yeah, maybe to do it quickly, we can have some MIDI stuff. So I will not do step by step, but I will just copy paste a patcher into this environment. So let's make a new one. Yeah, force patcher. And here we can have an example like guitar UI MIDI maybe, and directly connect it to output. So by default, I think it will basically enable the MIDI function, and maybe you will need some effects, general effects, which is a reverb. For that all the voices have the same effects group. So to enable this effect, you need to do like iterators, just connect it from its output to its input. So it will just compile the effect for you. So now we have a MIDI ready patcher. We'll call it MIDI. Then to test it in JS patcher, I will just put some code directly here. It will ask me if I allow to use MIDI devices, and yes. So here we have a bang. We have an object called MIDI devices. We have a menu, allows you to choose which MIDI devices you want to use. So here's my keyboard. Basically, it will display what I'm playing. And I will put my force patcher here. MIDI.pad. And so to enable the MIDI function, you need to specify the voices it will use. So here I will put 8. And audio out. There's a 2. And maybe some volume control before. Okay, I don't know why the cables are disappearing, but I think it works. And let's just connect with the merger to have two channels. Maybe this one. Yeah, merger before and now looking after. Oh, I should have. Oh, only have one output, so just duplicate them. Okay. Yeah, I think we don't have much time to do further. Yeah, it's just it. If you have any questions. Yeah.
Yeah. Super
I think
nice.
Albert have some
question.
Yes, Albert Graf from the University of Mainz. Well, awesome work. I'm really looking forward to trying this out in my courses. So I'd like to ask you, I was a bit late for the session, so maybe you said that at the beginning, but what is this written in? Is it just plain JavaScript, or do you need any other special tools?
Oh, yeah. So basically, we are only using JavaScript and Faust. It's just under, yeah. It's just my understand. Just I need to understand correctly how Faust works and how to form these expressions, and yeah, the rest is just combined from JavaScript. And yeah, this is an open source project, so you can have it on GitHub.
This runs under Chrome, so if you have Chrome running in any environment and have a JavaScript engine, you can make this work, right? Did I understand that correctly? So we could make it run directly in Pardata, for instance, because that has a built-in JavaScript engine. But for starters, if I want to install this on our own web server for the courses that I'm doing, can you quickly sketch out the steps that I'd have to do?
Oh yes. So basically, it doesn't have any server. It's just a web application that can be run standalone or just offline. If you fetch these codes from GitHub, you will just run it quickly. Yeah, just like that.
Okay, thank you. Very nice. Thank you very much.
Xiong, is it a progressive web app?
Yes,
okay.
You can actually install from Chrome. And I think from some Android mobile devices, you can also use it. I not tested, for instance, but yeah, I think it works.
Yeah, I know that the Faust IDE works on my phone, for example. But
yeah, it's
Michel?
just the creation of these boxes and the connections. I don't think it can be done easily with a mobile device.
Sure,
but,
sure.
Yeah.
Michel, yes? We can't hear you, Michel.
Can you hear me now?
Yes.
Yeah. Oh, not anymore. Yeah, maybe I can just
yes,
ask,
can you hear me?
Yeah.
Yes.
Is it better?
Yeah. Yes.
Micro. Hello.
We can hear you. We can.
Oh. Hello. Can you hear me?
Yes.
Okay. So because I have my sound card plugged. Okay. Well, my question was, can it work? Does it work on Firefox? Because yesterday I talked a lot with Paul Adenau from Web Audio, and he was really fed up of application that requires Chrome for web MIDI. He said, well, in Ableton, if you don't have a MIDI device, you can do audio project. So I wanted to be sure that it doesn't run only in Chrome.
Actually, it works on Firefox, but it's just one thing. It will not work is copy paste.
Okay.
So if you copy a part of patcher and paste otherwhere, you will have problems.
Okay, maybe you can exchange.
Part, yes.
Maybe you can exchange with Paul Adno in order to make this work, because he's now spending some time helping people making Chrome-only application work also on Firefox. So.
Okay. Yeah. Yeah, I need to respond to this documentation question because this is really experimental and pre-alpha, so I don't have any documentation written. And actually, I just fixed some bugs today. So yeah, just if you want to know more about it, just look at the code on GitHub. So yeah, maybe I can put the GitHub link here. Yeah. Okay, I will stop screen share.
Okay. Do we have any more questions for Xiong?
Just one remark, if I may. Could you upload the examples that you did today?
Oh, yeah, sure. I prepared that, but it's just I'm not showing you the examples. Yeah, I will also paste all these things on the chat.
I've got another question, maybe, Xiong. I know because we're working together that you will be able to import external graphs or external plugins into your patches. Can you say a little about this?
Yeah. So it's a little bit off topic because it's not for Faust, it's for JavaScript. So yeah, actually in JS Patcher you can use eternal like npm packages, to do more things like graphical processing or
I wasn't talking about this. I mean, you will be able to load web audio modules also written in Faust, for example.
Oh yeah.
Or can you also import gen patches or?
Yeah, good question. For web audio modules, yes. I don't know if I made the last modifications of the API here, but generally, if you have already written web audio module, it can be used as a plugin here.
Web audio modules are web audio plugins that you can export from the Faust IDE that can include a graphic user interface and that will run in WebAssembly. So you can add them directly in Xiong's tool. And about Gen?
Gen, it's a little bit complicated because Gen can do other things like buffer operating, or Gen can also do video stuff. So actually, I already ported a part of Gen into Faust. So in this link, you will find some Gen examples. It's just a copy paste to this Faust patcher, and it will just run. But you also have something that is not just import them and it can be run like this. So yeah, it's not simple like that.
Okay.
Thank you again, and bravo, frankly, wonderful work.
Thank you.
Thank you.
And so, if you want to see another presentation of this work by Xiong, then you can go to the International Faust Conference, the 1st and 2nd of December. Okay, so the next talk is by Stefan Letz. So Stefan is a full-time researcher at Gram. Is doing an amazing work since many years on Faust, on the tools, on the architecture, on animating the community, and his last production, so to speak, is a way to program VCV rack modules using Faust. So he's going to give us a workshop on how to do that. So Stefan.
Stefan, we cannot hear you. Activate your microphone.
Do you hear me and do you hear the sound?
It's good. Okay.
Yeah. And the sound?
Not much sound, I'm afraid.
Aha.
Maybe the noise filter filters it out or something.
It's a sinus. Do you see my screen? I'm just playing with VCV rack. We get some sound now.
No sign. At least not over here.
Uh-huh. Because I'm using an application loopback driver, which is supposed to share what I'm speaking and the sound coming from VCV rack. And so it's supposed to be on. Because if I cannot make sound coming from VCV, it will be less interesting for you, obviously. And do you have any idea of so, Jan? Yes. And here, no.
Jan, sorry, Stefan, can you have a look at your Meet preferences in your browser?
Yes. Maybe it's because I have to go to
parameters. Yeah.
I have to choose what I have to choose again.
No, you don't, leave that alone. That's the microphone input, just above.
Yes.
No, the one above. For the input, that's the output.
Stefan, move one up. There you go. There you were. One up.
One up, yeah.
One up?
Yeah.
The microphone. You need to switch the microphone input. There we go. So maybe the output from there we are.
So you have the sinus here?
Yes. Okay. But your voice is very low and very far.
Now, have a look at your loopback preferences. There's something there. Not there in loopback. You can modulate your sound. There you go. You can just beneath. Yeah, that's perfect. And beneath in options.
Is it better?
A little bit, yeah. And in options, you probably have a slider to lower, but to make it upwards. Just click on options.
Here I can change the internal. So how is it now? better for you? Or
It's better.
not there?
It's better.
It's better?
Not perfect,
Can
but
we try?
better.
We have to. So do I try this way, and you say me if you understand something? So basically, I'm going to follow the workshop page that can be started from the main site, PAW site page, and basically following this page that has already been written. And the point also was for you to possibly install rack and rack VCV SDK, and even possibly the VCV prototype, which is a module that you can program, and we have developed the first version for this VCV prototype. So assuming you have installed part of this, or maybe everything, you can try to do it yourself, what I'm going to present, otherwise you can just follow the workshop. So since we already had this nice presentation of VCV rack by Max this morning, I'm not going to explain the software anymore, and you understand so that it's VCV rack, it's a software emulation of modular synthesis module that you can connect quite freely. The interesting point is that it tries to mimic what you can do with hardware module by connecting CV, control, and audio, and mix everything. And in some sense, you can blur the usual distinction between audio signal and control signal that we have in audio software. We usually speak about control rate and audio rate. And in this kind of approach, you can basically blur the two kind of signal, which is quite interesting because you can have more flexibility in the way you describe your patch. When you are a programmer, you have to know some more precise stuff, because since this software emulation is basically an emulation of the voltage approach, you have to know that signals are going to vary in a specific range, like -5 and +5 volt, or 0, 10 volts. And MIDI signals usually follow this 1 volt per octave convention. And this has to be known when you start to program with VCV rack, because obviously you have to understand how the signals are going to be transmitted between modules. The other important thing to know is that obviously you can describe a monophonic module here, but you can also have a notion of polyphony. So some modules can transport polyphonic signals up to 16 channels, and on the user interface of VCV rack, you will see that you have a thicker cable that basically says that more signals than only one is transmitted by the given cable. And in this workshop, I'm going to show 3 different things. First, we are going to behave as a regular C++ programmer that would have to use C++ from scratch to describe, to program a VCV module and to compile it and to install it into the software. The point of this is to give you an idea of what is supposed to be done usually when you want to develop a VCV module. And then obviously we will explain how you can simplify all this process by using, in this case, the first language to describe your DSP. There is the VCV rack developer give you an SDK that you have to install and configure a bit. And then they give you some helper tools that you can use to create a kind of template, module template that you will be able to update and modify so that you implement a real DSP and the GUI that you also want to use to control your DSP. So I'm going to execute part of the tutorial. You can look at the tutorial which is on the VCV Rack site here. I'm basically simplifying a bit the procedure. So here you have a first command that you can do. I'm going to switch into another screen. Here I am into my VCV Rack SDK. I can create my module and do just use some default. And then at the end, what is created here is a new folder with some C++ code and a makefile that you can use to compile. Sorry, obviously you have to go inside the created folder and you have to make it to compile it. Now, an interesting point of this VCV Rack module is the fact that you can, as a programmer, you can describe the GUI using a completely SVG-based approach. So basically, you can use a standard graphical software like Inkscape to describe the GUI, and they have a kind of convention so that you can decide to have you will have audio input, audio output, control voltage input and output, and knobs, parameter, and switch, things like that. And you have a color by using the specific color, you can describe to the system that you are going to need this number of input, output, control voltage, and knob, and so on. And then they have a Python script. They will analyze this SVG file and basically create some C++ code for you to help you create the user interface. So we are going to do that. I have already taken this SVG file. I have it, it's not done by default, but I have basically to copy it into the res folder of my plugin. And my plugin is basically the template folder I just created before. Then I go back and I use another command that will now analyze this SVG file to create some additional C++ file. And you see here there is a new file that has been created automatically. And this file basically contains code which has been created automatically and that will create the user interface. And you see that this module defines a process function that is going to be called to produce the actual sample. Yes, I understand I forgot to say something. The important thing also about VCV Rack is that since you have this blur between audio and control, it means audio is computed sample by sample. So basically you have a buffer of only one sample. So it means the process function that we just saw is going to be called sample by sample. Now, if I want to put some real code, I'm going to copy paste this code, which basically is going to compute the sinus using a phasor signal, which is fed into a sinus function. I just copy this code. I have to uncomment some code into the template file. I don't know why it's not done by default, but it's done like that. You have to uncomment this. And then you go back into the folder you make, type make, and then you type make install. And when you type make install, the compile plugin, which is in this case, yes, it's a dynamic library on macOS, and everything will be transmitted on, will be installed into your VCV application. And you can now start VCV rack, and if everything works, then yes, you see here a new module. The module we just developed with C++, and that is supposed to output assignments. And since I've not even tried to use the button is not even just assignments given fixed frequency. So, as you see, this is a way to describe, to program your own module. Obviously, to do something more interesting, you have to take a bit of time to implement more complex DSP into the process function. And obviously, you may want to describe a more complex GUI. Again, you can use this Inkscape-based approach to describe the background and just add some button on top of the SVG background, or you can, if you want to, obviously in this kind of tool, you can do it completely by program. You can completely design your user interface by using C++ code. And this is something, obviously, we will have to do ourselves when we go to the force-based approach. Still okay for you? Yes? Yes? No feedback? Everything is working? Yeah, okay. So next step is now to show you what we have done to add forced development capabilities into VCV. So there is basically two ways to do that. One is by extending the VCV prototype module, which is a project that is also developed by Andrew Beltz, same guy who has developed the VCV rack application. And basically this project, which is on GitHub, gives you the capability to have a kind of template module with a fixed GUI with 6 input, 6 output, which can be either audio input, output, or CV input, output, 6 knobs, 6 lights, 6 switches that you can, which color you can control. And this VCV prototype can be programmed using either JavaScript, Lua, Volt, which is a domain-specific language, similar to Faust in some sense, or pure data. And obviously, what we have done here is adding Faust as a language that can be used into this VCV prototype along the other language that you can use at the same time, not exactly at the same time, but in the same session, you can possibly switch between JavaScript, Volt, Lua, and Faust. And as I explained just before, the user interface of this module is defined by advance. You cannot change it. You can only decide how you are going to use the switch, the knob, the input, audio input, output from 1 to 6, and how you are going to connect basically your DSP code to this user interface. To have Faust running into this VCV module, we use libforce, which is basically the library version of the Force compiler. And libforce can be used either with LLVM, JIT, or just-in-time compiler, so basically which allows to dynamically compile a DSP Force program on the fly and execute them in memory directly. But since deploying LLVM, it's always a bit of pain because you have to download a huge project and compile it. For this specific example, we decided to use another backend, which is part of the FAUST compilation chain, which is a pure interpreter that interprets some kind of bytecode that has been produced during the compilation step. And obviously that will run slower compared to LLVM, but it's fast enough to be used to prototype DSP code into this module. If you want to try it, since this FAUST development is not yet part of the official VCV prototype module, you have to use a FAUST branch on this project, and basically the FAUST branch, you have a FAUST implementation here, and you have additional documentation that right now is in a separate file that explain how you are going to use FAUST into this context, and we are going basically to use to follow part of this documentation. Yes, sorry, I switched from window to window. So as I explained just before, since you have this fixed GUI, it means you have to, as a programmer, you have to decide how will you connect and which switch or knobs or audio input you are going to connect to your DSP. And the way we do that in FAUST is using metadata. It has also been demonstrated this morning with the Gramophone project. Romain just demonstrate how you can use a switch or knob metadata to connect a given parameter into your FAUST code into a given hardware button on the gramophone. And in this case, it will be connected to a graphical element into the user interface. So basically, you can use switch from 1 to 6 to decide to connect a given parameter to a switch, which will correspond to a button or checkbox into FAUST user interface element. You can use knobs from 1 to 6, and you can use this lighting system, which have each 3 color components, red, green, blue, and by combining them, you can basically light with any color the elements that can be controlled with this coloring scheme, basically. And basically, you use it with output controller in the FAUST terminology, and output controller are basically a bar graph. So this is an example of a button that you would describe in FAUST syntax that would be connected to the switch number 1, and that will also be highlighted in red when you just hit the button, because basically the signal of the button is going through a bar graph, which is going to highlight in red. And here, a bit more complex example of where you can even connect to 3 different colors at the same time. We are going to look at some example. Here I have to cut and paste this code into the VCV prototype. How do I do that? I just copy here. I have the VCV prototype with FAUST support here. Probably I have to load I create a new DSP file. By default, this DSP file contains some default code. I'm just going to replace the default code with my code. And as soon as I save the file, it will be recompiled on the fly with the libfrost and the interpreter backend. And it's supposed to produce something. So I have to connect the output of this. So now we are, yeah, so it's working. So now we are trying to understand what this code is actually doing. So this code is basically outputting two different signals. This is the left signal, the right signal. The left signal is produced by an oscillator controlled by the frequency with a gain control. And here, as explained at the beginning, since we have to deal and to follow the VCV rack voltage convention, we have to multiply the output by 5. Basically, audio range goes between -5 and +5, and since audio signal generally goes from -1 to 1, just it means you have to multiply by 5. The right channel has a sawtooth signal multiplied by a gain and a gate here, which will allow to make the signal. Yeah, I guess you hear this. Here I can switch with the gate, which is basically a button. And I can maybe try to highlight using the hash paragraph. Also, maybe I have to, I am going to copy paste, it will be faster. And it's recompiled. And now when I hit the button, it's also colored by this red, which is quite nice. And as you see, as soon as I change, save, it's recompiling instantly. It's quite fast with the interpreter backend. And okay, this is the first example of code that we can have. A second, more complex, using CV input. Maybe I will directly switch to the third one, which is basically this VCO.dsp, which is basically a standard example of the VCV prototype that exists in JavaScript in Lua and that has been ported in Faust. So I think I can load it directly from here because it's part of the standard example. I can edit. So now I have this code, and so if we try to understand what it's doing, basically it's outputting a sinus, which is produced by multiplying a phasor, and this phasor is going to be has a frequency which is going to be the addition of two signals, something which is produced by a knob slider, so the first knobs here, and also a CV control, which will be the first CV input, which is going to be converted to a frequency value following this 1 volt per octave convention. So if I connect this, and if I connect like this signal here, so you see that the pitch is controlled at the same time as this button, but also with this sinus signal which is added, so you make this nice combination of the button And I am going also to demonstrate a MIDI controllable organ like DSP, which is also now part of the example. I can load it. It's an organ DSP. I have to edit it. And so, well, it's basically an organ done using additive synthesis. So for a given voice, you have the addition of 3 portions. You have a panner, you have an ADSR envelope with some fixed value that is going to be used. And you have here, you see that the process basically will be connected to 3 inputs: the pitch, the gate, the valve inputs. In this case, we want to use a VCV, CV inputs, which are going to control the frequency, the gate, and the velocity of the note. And then here, to convert between the pitch, which is going to follow this 1 volt by octave convention, we use this. Okay. Okay. Jan told me that I have to stop talking when I'm doing sound and control. Yes, so now I am going to connect. Here I have this MIDI CV input. I have to connect voltage, frequency, gate, velocity on the 3 different control voltage input, and assuming I have my keyboard here. Do I need to check the MIDI? Yeah, it's supposed to be. It's supposed to play something, but it doesn't play. Why? Yes. I see that it's playing, but I don't hear any sound. Yes, maybe you hear something. Do you hear something? Yeah, okay. So it's basically a monophonic. So it's a monophonic MIDI synthesizer. So you only have 1 voice. But you have this MIDI 1 voltage convention CV input running. And yes, maybe I forgot to say that in VCV prototype, you can only describe monophonic instrument or effect because, well, it's done like that. And doing polyphony at the VCV rack level, at the programming level, is a bit more complex. So they decided not to do that into this programmable module, and it explains also that you cannot do more than this simple organ. Going back to my page, yes, maybe I can show you something a bit more demanding. CPU at the CPU level, like this physical model that has been initially designed and programmed by Romain. And so it's a bell, a model of a bell. And here also I have done some connection of some part of the GUI. The gate of the bell to hit the bell is connected to the switch 1 button. You have a knobs that is connected to the gain, and then this bell is connected to a free verb, and the free verb also has some knobs that are connected to the VCV prototype UI. So if I hit the button here, I have, and here I also describe the fact that yes, the button becomes red when it's hit. And if you look at the CPU meter, so you see it takes a bit of CPU because, well, it's in interpreter mode, but while you have a physical model running into a free verb, and it's running in real time, sample by sample. It takes a bit of CPU, but it's usable. Okay. Next section concern this VCV, this Faust to VCV rack tool. So you probably know Faust to something tools that we have developed over the years, like Faust to VST, Faust to iOS, Faust to Android. So that basically allows to transform a given DSP program into a binary, a plugin, an application, depending of the target. So it's a work in progress, as you will see in a few minutes, but you can already use it to describe a monophonic or polyphonic instrument, and you can also use a sound file if you need to. And we have installed everything into the Faust IDE so that you can export ready to compile folder from a given DSP so that you can finish compilation on your own machine and then install the resulting program into VCV rack. In this development, we have done some alternative choice concerning this range adaptation. So in this case, the architecture choose to automatically do some conversion for you, so you don't have to multiply the output by 5 anymore. It's done by the C++ architecture file. Same for CV control. And we also, for the polyphonic case, we follow the Freq gain convention that you may know if you already developed with Faust. It's a way to describe a polyphonic aware, MIDI aware, and possibly polyphonic aware instrument by mapping the frequencies, the gate, and the gain coming typically from MIDI keyboards. In this case, since we are into this VCV model, we are going to automatically map the MIDI value with 1 volt by octave convention to the frequency which is expected on Faust DSP side. And you are going to use this envoice none parameter if you use Faust to VCV rack in a terminal to choose a number of voice you want, up to 16 voice since it's limited in VCV. And if you want to choose between, well, first, this Faust to VCV rack tool is going to create the GUI for you. So it will, as usual, analyze the DSP code and find out slider, button, switch, bar graph, and it is going to create a GUI. You will see that it's still a work in progress because you see the GUI is not so nice for now, but basically the idea is that the number of button and any kind of user interface item is going to be created automatically for you by the FOSS2 VCV rack tool. But if you want at some point to have a given control be connected to a CV input and not to a regular knobs, you can use this CV and metadata to connect to a given number of, well, the first or the second or the third, the index of the input you want to connect to your parameter. So if we take some code example, here you see that we have the FOSS2 VCV rack version of the first code we were looking at before. So this is this example with two different signal on left and right channel with the gain and gate button here and check button to hit to make the sound work. And here in this case I can directly use the FAUST IDE. So here it's supposed to, and I'm going to change a bit this so that we can edit the name of the code. I can possibly test it into FAUST IDE, and then I can export it. I have a new VCV rack platform and I have 3 different targets. You see that there is still a typo here. It ends by soul, but it's not to be related to soul at any. It's not related to soul, but it's a typo. And here I'm going to choose VCV rack, which is basically a monophonic target. I hit compile. I download the result. I have to close VCV rack. Each time you want to add a new module into VCV rack, you have to load it again so that it detects the module. So here I am going into my download folder. I have this binary folder. I can go into PAW1. PAW1 actually contains again the source code and the makefile, and you do make install. It compiles everything. It does install the resulting library into VCV rack. You open VCV rack, and now you see a new FAUST module. So you see this basic default GUI, but you know it's PAW1, and you can connect it, make it work, connect it, and it's supposed to work. You have the gate button. Okay, so basically it behaves like the VCV prototype version, but now you have the specific GUI which is generated for you with 2 buttons and 2 knobs. Yes, this is the first example. Sorry. Just to close my. Yes. So the second example I'm going to show is a bit more complex one with polyphony. Polyphony, it's here. So it's, well, again, similar to the organ version we had just before, but now we are going to generate a real polyphonic instrument. So again, doing that using the FAUST IDE. I think I have to do that to change again the name. So I can execute it. It's some additive synth with a master control, a panoramic, and 3 partial that you can control, exporting it. Here I'm exporting to polyphonic 16 DSP. Yes, I have to go there. I have to close. I have to uncompress. Second example. Compile it. Up. Install it in the civil rack. We'll remove this one. So I have this second one. So with a difference in user interface, I can connect this 3 control voltage inputs. And here I am supposed to use a real polyphonic mode. So I have to select here polyphonic 16 channels. So basically it means that each note we use in alternatively given cable into this 16 MIDI cable. And maybe I have to yes, because my velocity working, and I can connect maybe this. It's a 16 polyphonic instrument. And to finish the last example, if you want to connect this polyphonic instrument into an effect, then you have to compile a polyphonic effect, which can be done. Again, changing the name. So 3, compiling it, so it's a free verb, exporting it, 16 channel, compiling it, download, closing the VCB rack, compiling and installing the new module, reopening VCV again, installing this polyphonic reverb, connect my polyphonic cables here, and again. So as you see, it's still a work in progress. We have to improve the automatic GUI generation. We have to design a more beautiful layout and probably choose more beautiful buttons, and we have to design some specific widget, I guess. So this has to be known in this case completely using C++ code, because you cannot prepare the template, SVG template. So I think it's more or less time to finish the demo. I hope you were able to understand something and to hear something. And I can try to answer the question if you have some.
Thank you very much, Stéphane. It was an impressive demo because you did everything live,
Yes.
and it went quite well. So
yes, it's
well,
always a bit.
we had a little bit before that to restart the Faust service, and but that was okay. And so maybe there are questions.
Yes. About yes, I asked some question about the SDK. Yes, the SDK is completely separated from the application. One question is about how you produce the module. Well, in this case, we are getting the source of the module, and the source of the module is supposed to be, obviously you have to compile it for OS 6, Linux, and Windows each by each, but the makefile is supposed to be cross-platform. I've never tried right now. I only tried on OS 6, but the way the VCV Rack SDK is designed is that you are supposed to generate the binary for each platform you want to use. Yes. But you have to do it yourself. We may be able to produce some binary directly from the first compiler at some point, but it will take a bit more time to install everything on server side to be able to produce ready-to-use binaries. Yeah.
What is the difference of speed between the interpreted mode and the really compiled mode?
I guess it depends of the DSP. I would say between 3 and 15.
Okay.
Probably, yes. Yeah. It can be quite slow, but well, it's the nice thing is that compared to JavaScript or Lua, which are also interpreted language available into this VCV prototype, it's comparable or even faster in some cases. So since the point of this module is basically to prototype things, I think it's quite okay to use this interpreter. And again, it's much easier to deploy. This was the initial reason to use it instead of the LLVM. Okay.
Yeah, but we could imagine to have the LLVM version
yes.
also.
Obviously, I did the LLVM version. Right now, it's I can show you. Right now, it's defined into the code. Here I have, this is the code of this prototype. And here you can see that, yes, I have the both version. The DSP factory is the LLVM version, and this is the interpreter version. So you can possibly, if you are a developer, you can move from the LLVM to interpreter version just by defining this compile type flag. This is right now done like that, but obviously it works also with LLVM. I've already tried. Yes.
So the problem would be that
Stéphane, is so you have the LLVM version also working?
Yes, at least on OS 6. Yes.
That's great. The only gotcha there is that you have to be sure if you're running something in RAC that the LLVM versions don't collide. So
Yeah.
yeah.
Yeah. I had some discussion with Andrew, and I think he wants to have something not too complex to deploy.
Yes, I remember that. Yeah.
And he's already fighting to deploy a pure data engine for the pure data version.
Right.
So I guess if we can use the interpreter version for the regular version, it will be okay, probably for most users. And if a more demanding user want to compile the LLVM version, why not? But it's, yeah.
Is that in the repository of VCV-RAC, of VCV prototype, or?
Yes, it's a branch. It's a fourth branch into VCV prototype. So Andrew recently moved my pull request as a branch. So you have to switch to the fourth branch and you can try it. Yes.
Mm-hmm. But Stefan, we could also release this prototype module, a specific version of the prototype module that based on the LLVM version, without having it being part of the VCV rack, right?
I don't know exactly the status of. Well, it's
maybe it's not open source. You mean?
Yes, it's open source. Obviously, the VCV prototype it's on GitHub, but I'm not sure we can decide to have our own version of the prototype, the binary version of the prototype. I think the right way will be to be merged into the official version of this module, and so that it will be accessible for everybody, and even in Windows and in Linux, which will be quite well. This is the goal at the end, to have a binary version of this module available for the 3 platforms.
Yeah, but no one keeps you from distributing binaries for which you have the source code up.
Yes,
I mean, that's perfectly okay, and I know that my students would need some binaries to download if they want to use that.
Yeah. Okay, maybe
that would be if you just put it somewhere on the Faust website, or maybe. Right.
Okay.
Oh, there is an interesting question by Florian on the.
Yes. Maybe I'm not sure about what you mean by mixing audio port and CV port. Right now, what we can do at first level is decide if we want some parameters which are usually control rate parameter in Faust. In this model, we can decide to associate them with CV metadata. In this case, they become CV input. But they are not CV input at the same time as GUI elements. You have to choose one of the two possibilities. I'm not sure it correctly answers to your question, but maybe we can discuss that again. Well, to be honest, I'm quite new into this CV model, and I will be happy to have feedback from more advanced users of this model, and possibly the choice we made about this automatic mapping of CV values and range issue, and maybe we can have some help from more advanced users to see if we have to make the model more general or add some compilation option to choose between different models. It could be interesting to follow the discussion, yes.
Okay, so I think that we are perfectly in time. Thank you again, Stefan. It's really, really nice. And so we are going to have the last talk of the day. And so it's by Andrew Ikenberry, which is an electronic instrument designer, as founder of the music tech company 2HP, Qubit, and Electrosmith. He has been responsible for the release of more than 100 synthesizers and product that continue to be used by some of the top composers and sound designers in the industry. Prior to this role, he studied electronic production and design at the Berklee College of Music. And in this workshop, we will walk through the process of creating programs for the Daisy Patch Eurorack module. So, Andrew, it's your turn. Thank you. Stéphane, you need to stop sharing your screen. Okay.
All right. Hello. Can you hear me now?
Yes, perfect.
All right. Thanks, Jan. And thanks to Stefan and you guys for having me here. It's really great to be presenting this with you all. As Jan mentioned, I'm one of the founders of Electrosmith. We've only been around for a couple of years, but the big project that took over all of our time this year was the Daisy, which some of you may or may not be familiar with, but it's a really exciting new platform for us and for quite a bunch of other people that we've been talking to this year. And so I wanted to take this opportunity to present it in a modular context and program it in C++, which I will go over. So I made a video presentation that I will now play for you. Hello, everyone. We're going to walk through the process of creating a Car Plus Strong physical modeling voice. We're going to use the Daisy embedded platform inside of the Daisy Patch Eurorack module to accomplish this. So let's start with what is the Daisy. Daisy is an embedded platform specifically designed for music and audio applications. So we really wanted to address the specific needs that audio tends to have, which usually amounts to processor cycles, memory, and high fidelity audio in and out, specifically, or an audio codec in this particular case. And so we came up with this idea for the Daisy a couple years ago, worked on it quite a bit, and finally brought it to fruition February of this year, 2020, and we launched our Kickstarter, which did really well. The response to it was spectacular and was more than we even hoped for up front. So this shows you the Daisy right here. This is the brain of the platform, the Daisy seed. So this is the little dev board, kind of looks like a Teensy, but it's a little longer. You have two rows of headers. These come installed on the Daisy when you get it. So normally there's male headers here on this 1x20 strip. And you can program it over USB. This is the processor here. It's a STM32H7 series processor. It's very fast. It runs up to 480 megahertz. This is our SD RAM. You have up to 64 megabytes of SD RAM available, external SD RAM, in addition to the internal RAM, and then the audio codec. And we're using a really quite nice AKM audio codec, which has 192 24-bit processing, and altogether it really equates to some nice audio that's easy to set up, easy to flash, and easy to program, we would hope. And speaking of programming, there's a lot of ways you can program the Daisy. It's compatible with, you can export from PD, pure data. You can use C or C++. You can almost use MaxMSPGen, which we're about to have ready very soon. And a few other integrations are in the works. But today we're going to be using C++ along with our specific libraries, the libdaisy and daisy_sp libraries, which we'll get to in a moment. So, like I said, this is the Daisy seed, but we're going to be using the Daisy patch, which looks like this. And it's essentially just a fancy breakout for the Daisy seed. So you'll notice the seed sticks through the front panel here so that you can get your USB cable in, press the user and boot reset buttons, and then it breaks out all of the signals from the Daisy seed to standard Eurorack level signals. And so you'll have bipolar CV inputs, some gate inputs. Your audio is going to be converted from line level up to 10 volts peak to peak. And a couple other neat features here, an OLED display, SD card, and then we actually added a secondary codec on board the patch so that it has quad inputs and outputs. So it's really quite a fancy Eurorack platform, and it shows the full extent of what the DAISY seed can do. And if you're interested at all in the circuits of the DAISY patch, you can find it on our GitHub repo. The hardware GitHub repo is hosted on Electrosmith's organization page, and it's completely open source, so you can see how to convert your seed signals to any other level that you would want to use in different formats. And you're not restricted to Eurorack. We have a guitar pedal, the pod, which is just a little kind of portable USB powered solution, and then we have a little desktop synth, the DAISY Field. So you can check those out as well. For today, however, we're going to be programming the patch in C++. So let's go over the libraries that we're going to be using. First of all, we'll be using libdaisy. And this is essentially deals with the nitty-gritty of the chip itself. So it doesn't have anything to do with audio per se. Libdaisy is all about talking to the chip so that you don't have to deal with the extremely low-level aspects of it. So setting the GPIO high or low, talking to the audio codec, the SD-RAM, MIDI, all of this is going to be encapsulated into the libdaisy library. For those of you familiar with STM32, you'll probably know about the HAL, which is the provided library from STMicro. And we're rewrapping a lot of HAL functions into libdaisy to make it easier for our particular user base to make sense of. A little more of the audio organization, having the MIDI and the audio codec stuff wrapped up in terms that you would generally see in the audio world. And so that's libdaisy. You can find it here on our GitHub, MIT license. So feel free to check out all the code, use it, reuse it, so on and so forth. Very, very permissive MIT license on all the code that we supply so far, barring a couple of our DSP modules, which we'll get to next. The DAISY SP library is our DSP library, as you notice with the capital DSP. So this is our anything to do with actual audio and synthesis and effects and things of that nature are in our DAISY SP library. And we kept them separate because we really wanted each of these libraries to be able to fulfill their specific purpose to the best of their ability. And we didn't want the DAISY SP library to be restricted to only the embedded environment. So we wanted DAISY SP to be able to be used on a PC for testing, maybe on the web, maybe in a VST, all over the place, anywhere it could be used. And that's why we separated the two libraries. And so DAISY SP, it's written in C++. If I didn't mention that about libdaisy, it's also C and C++ code. You can find the list of the modules on the repo, which is really easy. If you go to our modules folder, so you'll see we have quite a few things spanning, basic synthesis blocks like an AD envelope, ADSR, all the way to biquad filters, bit crush, delay lines. So it really runs the gamut. Moog ladder, it's a ladder filter. A lot of really spectacular DSP code here that we have either created ourselves or ported from venerable programs like Csound or that we found on the web, things of that nature. Another fun thing to mention here is we do have our documentation available on the web. It's pretty easy to browse. You can see the list of classes, pick one that you wanted to use. It will tell you the available methods, gives you a description, goes into a little more detail here. So this is a really nice resource to have if you are using the DAISY SP library. The first step, if you were going to be receiving your DAISY for the first time, would be to head over to our Getting Started wiki page. You can find this from all of the product pages for the DAISY products have this link on them. It's also a nav item, I believe, on the Electrosmith website, but is just our DAISY wiki GitHub repo, and it will have all the resources necessary, tutorials, what have you, for doing various things with the DAISY. So the homepage is our default Getting Started. This particular page will walk you through how to download an example, flash it to your DAISY, or rather you'll flash it using the web programmer that we have, verify its function and make some sound. We're going to go a little bit deeper than that since we want to write our own code, and we're going to write the code, compile it, and then flash it. So the first step you would need to do is to set up your development environment for the Daisy specifically. Now, depending upon if you're on Windows or Mac OS X, this is going to be quite different, so it's a little bit beyond the scope of this particular video, but if you are interested, you can follow this wiki page. It's not particularly difficult. We're using open source tools for what we are achieving. If you're familiar with GitHub, it will be much easier, and a couple command line applications, or a couple command line utilities that we're using for doing the compilation and flashing. Knowledge of those would be useful, but not necessarily required for getting going here. Our documentation should be pretty clear, and you can always access the Daisy forum or the Daisy Slack workspace if you have questions in that regard. So you'd follow this and install your development environment, and you'd be able to test it by compiling the Blink program, and you would not receive any errors, and you would know that you're good to go. So we're going to assume for this case that you've already done that step, because I've already done that on my computer, and we're going to move on to the code section. So for today's video, we're going to be using VS Code. You could use any IDE you want for this, of course. Sublime Text is a really popular solution. You could use Visual Studio if you're already familiar with that. VS Code is a new thing Microsoft came out with, which is like a slimmed down open source version of Visual Studio, which we're liking a lot, especially for people who are wondering which IDE to use for Daisy. It's a lot simpler than Visual Studio, which tends to be better for a lot of the use cases we're going to be dealing with here. And you can also access some debugging. We won't really go into that today, but you can find some helpful tips for that in our user base about setting up debugging with VS Code. So if you wanted to use this IDE, you could just go to code.visualstudio.com, and it's cross-platform, it's free, it's nice and easy, painless to install, really quick. If you've ever installed Visual Studio, this is the complete opposite experience. It's very easy and simple to get up and running with. So I already have mine installed, but you would be able to just go ahead and do that on your own. Next, if you set up your development environment, you would have cloned our Daisy examples GitHub repo. We can just check that out real quick. This is what houses all of the example programs for the Daisy, whichever hardware platform you're interested in. So when you're setting up your development toolchain, the way we usually teach that is to clone this with the submodules already for libdaisy and daisy.sp. You'll see those here. And then build the libraries and then start from there. And so we're assuming that we've already accomplished that. This is our Daisy examples repo here. We go into the patch folder. We'll see we have all of our Daisy patch example programs. Today we're going to be dealing with the pluck echo program. And so we would go here, and you can open this entire directory in VS Code, which would take you here. So then you can see, you can browse the make file, the CPP, and any other files that were in the directory. We are only interested in the CPP file, the C++ file. It is a single file example program. It's not too complicated, but there are some things. It's got a few different aspects to it. Primarily concerned with the fact that there is a display, there is the carpless strong synthesis, but there's also a delay line happening inside of the code, which adds a little bit of complexity to it, but it's really not too difficult, and we're going to walk through it line by line. So let's actually dig into a little sound demo of the pluck echo example program before looking at the code, so that when we're looking at it, we have an idea in our head of what it's going to sound like and how all the various pieces attach together. So let's pull up our Daisy patch here. So we have our Daisy patch. I've already flashed it with the pluck echo example program, but we will walk through that process as well once we're done examining and building the code ourselves. So I have the pluck echo loaded onto the Daisy seed, which is plugged into the Daisy patch, and it's in my Euro rack ready to go. So let's check out what that sounds like. If I press the encoder, it's going to trigger a note. And if I take a clock signal from the bloom and put it into gate in1, it's going to trigger it continuously. So here we have a nice low car plus strong note being triggered at a specific frequency. our controls are all here. So control 1 is our coarse frequency. So you hear it changing the pitch. Control 2 is our decay time. So this is going to be the length of the note. And then controls 3 and 4 correspond to our echo, or our delay line that we have. Control 3 is the delay time. Scrubbing effect there. And then control 4 is going to be our feedback. That's the example program. It's a very basic program. The control levels themselves are mapped to these little bars on the OLED, so you can see what they're set at quickly. And that's basically it. So let's check out the code now that we know what the end result is. So I'm just going to go top to bottom. And if you're familiar with C++, this should all be relatively straightforward. Even if not, I'd like to think that the code is still easy to understand in light of the fact that you understand what the instrument is in the end. So let's just dive right in. Right at the top, we have our includes. These are really straightforward. The daisypatch.h file really just offers a lot of easy functions, just utilities for dealing with the seed in the Eurorack world, rather than having to do these seed functions yourself, if that makes sense. So we can go ahead and take a look at the daisypatch file itself. What the daisypatch includes is the daisy seed, and then it just encapsulates a lot of utility functions mapped to the controls already, so you don't have to worry about which ADC input knob 1 is connected to, or which GPIO is controlling the OLED display, for example, things like that. So if you scroll through here, you'll see we have our daisy patch object. We have the start audio function, and you'll see things about the controls, update analog controls. So these are not seed functions because the seed doesn't have any analog controls by default, but the patch has a number of analog controls, which we would want to loop through at a specific frequency. And so we give a lot of just helper functions in the daisy patch, BSP we call it, board support. And so that's what that include is for. Let's go, lost ourselves. Here we go, pluck echo. Beneath that we have the daisy.sp header file, which just gives us access to all of our DSP modules that we're going to be using. And then string, of course, is so that we can deal with character arrays and send them to the OLED easily. Beneath that, we have our namespaces. So if you've used C++, this should be really simple. Daisy is our libdaisy namespace, and then daisy.sp is our daisy.sp namespace. This just helps prevent naming conflicts within our program, and so that we can access certain aspects of the libraries in a simpler syntax than we would have to do otherwise. These next defines are just simple macros to make the rest of our code a little more readable. Num voices is set to 32, so you can have up to 32 individual voices in this of this pluck instrument. So Daisy is really powerful. It can handle a lot of notes of polyphony. You'll come to find it's really capable of handling kind of these really larger than you'd ever need in the real world polyphony sizes. We don't really want to hear 32 notes of this pluck instrument, but it's nice to know that we could if we wanted to. Max delay, this is just setting the maximum time of our delay line. Our sample rate is 48K, so this is a 10-second max delay time that we're setting here. Okay, beneath that, we have our daisy patch object called HW, which stands for hardware. So thanks to our daisy patch header file, we have a class called daisy patch, and we're going to create an object called HW, which is a daisy patch object. So this is going to be our little handler for talking to the patch hardware itself from within our code, and it will make our syntax nice and easy when we want to do things like access knob 1, because we can do daisy patch.knob1, so on and so forth, and deal with our access or setters and getters through this daisy patch object. Beneath that, we are creating our polypluck object, which is a daisy SP module. And if you're not used to the syntax, this is a template. So it just allows code reusability. Basically in C++, it's a neat feature, which we use pretty sparingly. We don't use it all over the place, although I think this program does have 2 of them. Yeah, delay line is also a template. But you can read more on C++ templates if you want to dive into that, but suffice it to say it allows type agnostic creation and code reusability. So in this case, the polypluck, we can go to our definition there, and this is our daisy SP module. This is the file for that. So we're creating a polypluck class. Inside, we're probably going to be creating some other pluck type modules to create the polypluck. I did not write this particular one. Looks like Stephen Hensley did. So let's just scroll down it and see where it's created. So at the very bottom, you'll see a pluck object being created. And so there's also a daisy SP module called pluck, which is the core Carplus strong implementation in our library. The polypluck just gives you a polyphonic version of that module, and it's sort of like a meta module. It just includes the pluck inside of it and makes it easier for you, the user, to create a polyphonic instrument without having to deal with all of the voice allocation aspects. If you were going to create the polypluck from scratch, you'd have to do all of this fancy active voice settings, so on and so forth from within your code. And that's the polypluck class. So we can go back to our pluck echo now. So you'll see we're just telling the polypluck how many voices we want, and we already defined our num voices up here to 32. So we're saying create a polypluck object called synth, and it's going to have a max polyphony of 32 voices. Below that is our delay line object, which is just a simple delay line. This is in our daisy SP library as well. So you'll see, what did I do here?
Yeah, you're right. I was clicking the right thing, but it moves on now here. So
that is our polypluck object.
Yeah,
we created a polypluck object called synth, which has a max number of voices of 32 voices, which we already defined in our macro up here. Beneath that, we have our delay line, and so we're using a DSP object, daisy SP object called delay line, and we're creating an object named delay. So if we wanted to look at the definition for this, we could go over here. Just a standard delay line. This is accessible from within daisy SP. You can use it in a number of ways. Like I said, it's a template, so you can use different types of data for your audio buffer, which makes it a really handy thing all around. Beneath that, we have a reverb object, reverb SC. This was ported from C Sound, and that just gives us a little end-of-chain reverb that we're going to run the sound through, even though we don't have controls dedicated to the reverb specifically. And so at this point, we've included all the files that we need to, created some helpful macros, and created the objects that we need for the rest of our program to exist. And we make these objects live globally so that they exist in our main loop, but also inside of our callback. That's why these are global variables. And then beneath that, the one other variable that we need in both functions is the smooth time. And we'll get to this a little later, but it's essentially just a value we're going to run through a filter to smooth out the changes of the delay so you don't get a lot of zippers and crackles and pops and other audio artifacts that you would otherwise have happening. So Let's skip the audio callback for now and go to where the program actually starts running, which is our main function. If you've done any Arduino programming, you'll realize you have your setup and your loop, and this is essentially the setup of our program. So as soon as the chip boots up, it's going to come into main. It's going to do all of our initializations. It's going to hit this for loop where it just loops forever, and that's when our callback is going to take over and start running. So right now, we're just going to handle all of our initializations and tell everything what we want it to be before the audio starts being generated. So let's just start at the top. Sample rate. This is going to be the sample rate that we set for our audio. Hardware.init. You'll recall this hardware is our daisy patch object, and you can access the init method just through this simple syntax, hardware.init. And then let's actually take a look at that just so we can understand what's happening here. So the init method is going to handle all of the initialization for the daisy seed that we don't actually have to worry about, but we understand is necessary since we're in the patch environment. And so you'll see within the patch, it's going to configure the seed, it's going to set our block size, init the audio, the display. The display would not be on a pod, for example. CV outputs, the pod would also not have CV outputs, so on and so forth. MIDI, and all the way up down to a couple more screen things. And if you wanted to create your own URAC module using the daisy seed, the daisy patch class is a great place to start because you can take all of these functions and wrap them however you want according to your own hardware configuration. And that's what's in the hardware.init method. You don't have to worry about it too much. Just call it, and it's going to do what you want it to do. Make it really easy. Sample rate. There's two ways to deal with this. We're taking the default sample rate of our session, which is going to be 48 kilohertz. That's just what the seed's default is, and so we're okay with that. So what we're basically saying is, hey, return audio.sample rate, hardware.audio sample rate. It's going to say, okay, it's 48K, and we're going to assign that to sample rate. And then we can tell all of our other objects what the sample rate is. There are also methods that would allow you to set the sample rate. So you could set it to anything you wanted. Well, you can set it to what our library, the default options that we give you, which I think right now is, I can't remember exactly, but it's 8, 16, 32, 48, 96, something along those lines. But for now, we're just going to make it simple, and we're just going to say, whatever the default sample rate is, give me that, and I'm going to pass this value around where it needs to go. Beneath that, we have our display initialization. So we're going to create a string that just contains pluck echo, it's just the name of the program. We're going to format that, and then we're going to write to the display right during the init. And you'll notice when we flash our program, it's going to pop up and say pluck echo, and it's never going to say that again. And that's because we have that in our init function. This never gets called again. It just happens right when it starts running the first time. Hardware.display.update. This just causes whatever value you push to your display buffer to be updated on the screen. And then we create a little delay just to give the screen itself some time to compensate for that. Beneath that, we move on back to our synthesis. And so we're going to initialize our pluck echo object by calling the init function. And the only argument required for that is sample rate. So we pass in our sample rate, which we already got returned from our seed object, or via the patch. We got our sample rate. We're going to initialize the delay, which doesn't need the sample rate in its init function, but we are going to set the default delay time to our sample rate times 0.8, which equates to a half-second delay here. And then lastly, we have our reverb initializations. It needs to know the sample rate, and then you don't have to set these other things. It would just default to what it picked, but we have a couple of just default settings for the sound here. And we're not actually going to touch these because we don't have any controls mapped to our reverb as it is. Beneath that, we're going to start the ADC and the audio. And so the ADC here, just to be clear, is not actually referring to the audio analog to digital conversion. This is referring to the control analog to digital conversion. So the daisy seed itself has 16-bit ADC inputs for controls. So these are not something you're going to want to use for audio. They're not designed to be used for audio, but they are extremely high resolution control ADCs. So they're going to be read at a slower rate. you can read it at audio rate, but it's really designed to be, normally the typical rate here would be your control rate, which is usually once per sample period, but not at your sample rate. Or once at your callback rate, not at your sample rate, rather. And so we're saying start the ADCs, and so it's going to start reading all the values from our pots and our CVs and our gates. And then we're going to say start the audio, and we're going to tell it which function to use for our callback. So whatever function you tell it here, it's going to run that at the specified frequency. After that, we just create our, basically just an endless while loop. It's a for loop, but it just runs forever and continues to call the display controls function, which is why we see our controls mapped to the patch's OLED display. And display controls is a patch method. We don't have to write it ourselves. So it's a really useful thing for you to use in your own code if you want to just display the controls if you're debugging or if it's just useful. You can call the hardware.displayControls method, and it's going to handle all of that for you. That is the initialization section and our whole main function. Now let's check out the audio callback, which will be being called by the chip at a set frequency that we already set up in our init. So we'll go to the top here to the audio callback, which we already passed in as the name of the function that is going to be called. So if you're familiar with audio programming at all in C or C++, you've seen this. It's a really common format. You have your input buffer, output buffer. We're using floats because we have an FPU on board the chip, so we can do it with any processing penalties. And then this is just the size that we're going to be looping through of our buffer. So at the top, we have all of our local variables. These exist within inside of the callback, but they're going to be deallocated at the end of it. That's important to keep in mind. Beneath that, we have our buffers. These are just for readability for us to be easier to read the code and write to and from the input and output buffers, in this case, just the output. And then beneath that, we are going to handle our controls. And so this is an important thing to talk about here. We are going to do this at what would be considered sort of a standard control rate. So once every 48,000 samples, since this is our sample rate, once every 48,000 samples, we're going to update our controls.
So I wanted to pause briefly here and just mention that I misspoke. It's once per block, not once per 48,000 samples. So it's far more often than would be led to be believed by the misspeak there. So once per block size is the control rate.
Our pots, our CVs, our gates, so on and so forth. We don't want to update these at the audio rate because it would put a pretty severe strain on the CPU, and we don't need to. There may be a time when you need to put certain controls inside of the actual callback rate. This is not one of those times, so I won't really dig into that here. So suffice it to say that we're going to be doing that outside of the actual for loop, which generates our audio. So these are some very handy patch functions, debounce controls and update analog controls. The first one, debounce, if you're not familiar with that term, it is basically to eliminate any noise that will happen on switches when you're changing state. So if you go from high to low, there's going to be a few milliseconds where you could have some spurious on-off signals, and this just allows a settling period before reading that value. Beneath that, the update analog controls is going to loop through all of the patch controls that it already knows about because it knows about the DAISY patch, and it's going to process that ADC and return the value into the patches controls so that we can then access them later and assign them to our own variables as necessary. So that's going to handle all of that. Once we go beneath that, we can handle our triggering of the voice. There are two ways you can do that with this program, via the encoder. If you press the encoder, it will trigger a note, or the gate input. And so the encoder is a very simple syntax, hardware.encoder.rising edge. This will return true if it's currently sensing a rising edge, or the gate input is high. And so we can access the gate input via the hardware.gate input, and then you need to tell it which gate input we're talking about. And so that is this particular part here, gate in 1.trig. This will return true. If trig is high, it's going to return true, and that would trigger this if statement to also trigger our local variable to be a 1. Beneath that, we are doing some scaling, reading and scaling for our frequency value, the poly pluck object itself wants its frequency set in MIDI notes. And so what we're going to do first is hardware.get control value, control 1. This is going to return the ADC value that was already read and return it. And then we're going to scale that value between our MIDI note range and assign it to NN for new note. That's what that stands for. And then we're just going to quantize it to semitones. That's what this cast is doing here. So we now have an NN variable which features our control 1 value mapped to a range that our Daisy SP object wants it in. Beneath that, we set up our decay value for the pluck object, and it's very similar. You should get used to this by now. Get control value, but we're going to set it to control 2, and then we're just going to scale it between the range that we want, and that's what these two numbers are, and then assign that back to our local decay variable. And then once we've done that, we can then assign it to our actual pluck object, synth.setDecay, and then we just pass in our decay variable. Beneath that, same exact thing, but we're going to do it for the delay. It's a little more complex. There's a little more math scaling here, just due to the nature of how we want to scale it. But we're getting our control 3 value. We're putting that in a decay val, and then we're doing some math here to scale that range to the delay time range that we actually want. And then we're doing the same thing for feedback. And then we're going to apply those lower into our actual delay, but we do that at the callback rate so that we can minimize audio artifacts. Now we have our synthesis section. So this is where we actually fill up the output audio buffer before passing it along through the audio codec. So it's just a for loop, which is going to loop through each sample according to your size and then pass it into the output buffers. So first up, we have our delay. We're going to smooth out the delay time through a one-pole filter. That's what phone pole is. And then we're going to use that new filtered value and pass it into the set delay setter method on the delay object. The reason we do this in the audio callback is to reduce any zipper sounds or other audio artifacts that may occur if you ran it at the control rate, which is much slower. Beneath that, we're going to generate the actual plucked note. And to do that, we're going to call the process method, which returns one sample from a Daisy SP object. They all have the same process method, and that just returns one sample, which you can store into a local variable. Beneath that, we have our delay line, which is a very similar thing. We're going to take our signal and multiply our wet delay signal times its feedback, add those together, and then pass that into delay.write, which is just a method for writing to our delay line. Beneath that, we have our reverb send. So we're going to do a very similar thing where we're going to add the dry and the wet together, scale them, and pass it into the reverb. And then last but not least, we just assign it to the actual output buffers themselves. So we're going to take our dry signal, add it to our wet signal, and pass it into the left, and then do the same thing for the right. And at that point, our output buffers will be filled up at the sample rate and then dumped out to the audio codec in time to be sent out to the actual Daisy outputs. So that is the program in its entirety. It's relatively straightforward. Thanks to all of the abstraction, we have quite readable code, in my opinion. And it enables us to take a more musical approach to the code than it would be if we had to write all of this from scratch every time, which is the benefit of using the Daisy SP and libdaisy libraries. So now, let's flash this program to our Daisy patch and take a musical listen to it. So for that, we will go to the Daisy web programmer. You can access this from our website, or if you know the URL, you can just grab it here. Now, what we need to do is put these Daisy seed into bootloader mode, and which means it's ready to accept firmware. We'll connect to it, flash the firmware, and we'll be good to go. It's important to note you need to use Chrome in order to use the web programmer. It's cross-platform, but it does need Chrome, and if you're on Windows, you may need to update your USB driver, which we also have a wiki page on. So what we're going to do is we're going to head over to our Daisy patch, and we're going to press the boot button. We're going to hold it down, and then we're going to press the reset button. Once you've pressed the reset, you can let go of boot, and it's now in bootloader mode. So when we hit the connect button here on our web programmer, you're going to see something called DFU in FS mode. This is the Daisy seed. So select that, hit connect, And now we're connected. So now we can select the firmware that we want to upload and flash it to the Daisy. So we're going to say patch for our platform and pluck echo for our example. Now all you need to do is hit program. It's going to give you a little progress bar. And it'll tell us once it's done. There we go. All done. And so that took place over the micro USB cable here. And we didn't need any intermediary hardware going between our computer and the dev board. One other thing to note, just our web programmer, we try and flush out each examples page with some useful information. So at the top, you'll see a little table of the controls, a little diagram showing you what corresponds to what. And sometimes we'll have a little video snippet down here, maybe a SoundCloud example. We don't have that for this one, but we do for a couple of the other ones. Okay. Now that we've flashed the code, let's take another listen and try and explore this in a little bit more of a musical context, maybe. All right, so we'll patch in our clock signal from the Bloom. There we go, our plucked voice. And let's now take our sequence signal out. So this is a vocal octave sequence. We'll plug it into control 1, which is our pitch. And we'll hear the pitch changing. So that's nice, get some delay. Let's now patch in some random voltage. We're going to grab it from the chance, which is out of screen, but we'll put that into our decay. So you'll notice our decay is changing. Now we'll take some more random voltage. We'll plug that into our delay time. And then we'll grab some smooth random voltage, plug that into our feedback. So this is just 3 modules, and you'll see we're getting quite a lot of results for the few things that we had to do here, because a lot of the DSP is just encapsulated in the Daisy patch, and we're able to take advantage of these a multitude of processing effects localized to a single module, just apply some CV, some modulation, and we can get quite a wide range of sounds in the output. I hope that was helpful. Thanks for watching.
Thanks. I can, yeah, if there's any questions, I'd be happy to field them now. Should I stop presenting? But yeah, I'd be happy to answer any questions anybody has. Yeah, I would love to give some updates on that too. So I saw Stefan asked about the Gen export. So we have a lot of great news on that this week. Actually, we went into our internal beta on that, and so we've been flushing out just minor platform inconsistencies between Windows and Mac OS X. But we are expecting to do a smaller public beta next week on the Gen export, and so I know a lot of people have been waiting for that. That should be really exciting. And it really turned out pretty spectacular. There's a lot of unique features to the Gen export. You can load in a bunch of different patches at a time, all onto the same program. And so it's almost as if you're running like 10 programs at once onto the Daisy. And so keep an eye out for that next week. We should have some updates for that. And then as far as the Faust integration goes, one of the next big things on our roadmap that I think Faust is waiting on is getting code execution from our QuadSpy storage. One of the things about the Daisy is the particular processor has a smaller amount of internal flash memory, which is where you usually execute code from. This is what enables us to sell it at a nice price point. However, it makes it a little more difficult to load in large programs. So if you're writing little embedded modular or guitar pedal programs, no problem. But as soon as you want to integrate a larger, more sophisticated language like Faust, you're going to need a little more flash memory. And so we did put a 8 megabyte QuadSpy chip on there, and then we can execute code from that chip. We just haven't added all the drivers to do so. But that is coming up in the next month or so on our roadmap, and then hopefully we can move forward working with Stefan on the Faust integration. Yeah.
Yes. I can maybe comment. So we have now, do you hear me? Yes. We have received two different models. We have a pod action sent by you, Andrew, and your colleague, I guess. And we had also a guy just sending us a patch just because we are I don't know, he was a gift in some sense. And we need to expand our architecture file to be able to program any model, because right now it's not expressive enough to be able to do that. So I have to work on other model. And the second point is yes, the size of C++ that we export, but basically not exactly our code, but as soon as we use IO stream, for instance, it adds some big bunch of code. So maybe either we have to remove some or rewrite some of our architecture file. So it may be a way to improve that. Or if, as you said, if you improve the situation or your side, it will be easier for other projects also. So maybe it makes sense.
Yeah, definitely. And just regarding to the model comment that you made, we're working on documenting each specific type of hardware with a JSON file, because we have the patch, the pod, so on and so forth. So all of the controls are going to be mapped in a JSON file, which we're then going to try and use. And we've been doing this for Gen, where it kind of knows which controls to already map based on the board specification in the JSON.
So it means by reading the JSON, we could have a kind of generic system that would adapt to a given hardware. So maybe it's the way to go. Yes. Okay.
Right.
Okay. Thanks. Yeah. In a more generic way. Otherwise, we have to tweak the code each time. So yes. One way to have, we were thinking at some point with a kind of CSS model, when you could separate this kind of description in a kind of separated file, so that you could trying to avoid having this part of the connection done directly into the source code. So this is a way to think about. But now, since we have now a lot of people trying to use Faust into the embedded world domain, Teensy, SP32, Daisy, Bella, the problem Common Core, and also old. So we have to find a generic solution, otherwise it will. It is the time to try to find a better way to do. There is also another question that we have to solve. It's a memory allocation issue. It's somewhat separated from the C++ code size. In Faust, right now, we just generate a flat memory region for the complete DSP, including delay lines. But obviously, at some point, this size is too much for the local memory, and you may have to decide that like the long delay line would have to be allocated at another place. And so to do that, we will probably one way to do that will be to give an option into the compiler to add a kind of memory allocator that you can change, so that the memory allocator would decide where to put each kind of memory. So this is something also that we have to think in a generic way, so that it would adapt to any kind of embedded device. Yes, yeah, because it's also the same issue with Teensy and so on.
Yeah, that's the first thing that everyone coming from a desktop programming background is confused about. They're always confused because they say, "Hey, I'm trying to do this thing with my buffers and whatever," and we have to tell them, "Hey, this is a different world than you're used to. You actually have to keep the memory aspect in mind because it's so limited. You don't have endless buffers and memory and RAM and everything." So it's definitely a shock for a lot of people. But
so maybe I have another question. We will start in a few months a project that will be sponsored by the National Research Agency here in France about using FPGAs. So what is your position as a hardware developer about FPGAs and ultra low latency and
So FPGAs are something we discussed a few years back. They're obviously, a spectacular solution to DSP hardware, and it really comes down to what your goals are in the end. For us, our choice of microcontroller was very specific because we needed it to be, one, an open platform, and B, we wanted to support as generic of a solution as possible so that you could add all the things you want. So what I'm talking about here is things like USB support, wireless connectivity, GPIO, things of that nature. So when you're looking at the audio hardware landscape, you're going to have a lot of options which have a lot of processing power, but the openness of their tools, the available free tool chains and flashing applications that you can use are not always available. So in that regard, things like the Shark processors, they're extremely powerful, but if you want to have all these other open aspects about it or allow people to have a lot of freedom, it's probably not the way to go because it requires a proprietary IDE, flashing set, things like that. FPGAs are a little similar in that regard, not necessarily that it's all closed, but it becomes a little more difficult to program, which makes it a little less flexible, which was why we ultimately decided for the Daisy to go the route of the STM32 series processors because people are so familiar with it. There's so many free tools available, and it just gives you all these things for free, like being able to flash firmware over the web through USB. We didn't have to do a whole lot of work to implement that, which was really a big selling point for us. So I know FPGAs are a spectacular solution for DSP. It really just depends about the other added benefits that come with the platform choice overall.
Are there any other questions?
And that brings up another good point too. I mean, there's another really popular chip you guys some of you may be familiar with the FV1 by Spin Semiconductor. It's a really popular chip. It's similar. It's a really great DSP chip, but you can only program it in assembly code. And so the flexibility and the programmable nature of the FV1 is one of the big drawbacks to it. So it's a great solution for a lot of problems, and a lot of people, they have no complaints. But if you can only program something in one specific way, it limits the range of uses and places that it's going to wind up being used. So it's well similar.
Hey, thanks for the great presentation, Andrew. Today, is it possible to run the code on a PC or Mac, like to test, to prototype, before flashing the DAISY?
That's a great question. I'm glad you asked that. So it's not possible yet, but we are very close to implementing something like that. And we are actually working on potentially doing a VCV rack module, which will let you prototype DAISY designs in VCV rack, and then you can export it to your DAISY once you've ironed out all the kinks. So that's one way that should be available pretty soon. And of course, we're working on that because we use DAISY day in, day out for our other projects, for other products we're releasing. And so we'd like to be able to develop at a higher level before worrying about performance constraints or anything like that, and iron out whether or not it's a good instrument from a musical perspective before ironing out and working on bugs and low-level problems that we don't necessarily need to handle at that point in time.
Okay. Are there any other questions? So, Romain, how was the truffade? Is it Romain still here?
So Roland, yeah, that's a great question. We haven't actually had anybody ask that question yet. I'm kind of surprised. Yeah, I'm sure that we will be supporting that at some point in time, and we'll make some tutorials to do it. We've never done it ourselves, actually. So 480 has been enough for all the things we wanted to do. So I will, yeah, let me talk with Steven about that. We can see about making some examples on how to do that. But that's a great question.
Okay, so personally, I found this was a very exciting day, and I would like to thank all the speakers. I think really the presentation were really incredible and very full of information and details, and I think that we will go back to the video recording with a lot of benefit and review again and again all these presentations. So, and I will really like to thank you very much, all the presenters. Some of them had to wake up very early in the morning, Andrew, and some of them had to go to bed very late from China, and Xiong, for example. So obviously it was an edition a little bit strange, like all the workshop and conferences in this moment. And for doing hands-on workshop, it's not the best situation. I think we had issues with the sound quality, and sometimes was not completely understandable, but that's the situation. So we will have to wait one more year, and hopefully we can do that in a more traditional situation. But probably we will. The other edition of PAW were not streamed at all, and which was also not very good. So probably the next edition will have a mixture of streaming, live chat, etc. There's a lot of very interesting things that happen when we see each other like this. We can chat and share the screens, etc. That you don't have if you are in a room and one person presenting. So we need to find a smart combination of the old and new world, so to speak. Okay, so thank you all very much. I will keep you updated about the edition of the the streamed version on YouTube. I hope it's not too bad, and I will probably slice it in for each workshop and put the reference in the link into the PAW website. So, anybody has something to say? So, Albert?
Yeah, and it was a great conference.
Okay, no, but you are complaining about the receipt of...
No, I just wanted to remind Romain that he maybe sends the recipe to Peter Kirn, who volunteers to put it up on his article on this conference.
I will definitely send it his way. And I also made a video of the final product after the aperitif. So we will post that as well.
Do you plan to post some samples of the final product?
Can we paste it?
Yeah, we can mail it to you, Albert, if you want.
Great.
Okay, so thank you, everybody.
Bye-bye, everybody.
Thanks again to all the speakers.
Bye-bye.
And it was, super interesting.
Bye, guys.
Super interesting. Bye-bye.
Thank you.